Okay, Arun, it's now yours.
Thank you very much, Carl. Greetings, everyone. My name is Arun Ross. I'm with Michigan State University, and I'm very pleased to welcome each one of you to this third workshop on demographic variations in the performance of biometrics and related technology that is being co-organized by Kevin Boyer from the University of Notre Dame, Michael King from Florida Institute of Technology, Carl Rixenek from Lapitus Solutions, Nisha Srinivas from TrueFace, and we're very happy to host this workshop under the umbrella of WACV 2022. This is a very important and I would dare say timely topic. There is much discussion even in society about what we call as demographic differentials in the performance of biometrics. And some would even say that there are biases in the system. And so one of the goals of this workshop is to understand the nature of these differentials that we see in biometrics and related technology, but also ways in which these differentials can be mitigated in order to ensure that there is algorithmic fairness across different demographic groups. And so in some cases, we have to anticipate what the nature of these variations will be across demographic groups and also to mitigate their effect and their impact. So that is the primary goal of this workshop. So in this spirit, we have three papers that address various aspects of algorithmic fairness in some biometric problems. And at the same time, these are augmented with some keynote talks. We're very pleased to have these keynote talks. In fact, after the first presentation by Raghavendra, we will have the first keynote talk by Kush Varshney, and the topic is results in trustworthy machine learning that go against conventional wisdom. We have another keynote talk by Nisha Srinivas, exploring new dimensions of face recognition bias. Then by Kevin Boyer, finding causes of demographic accuracy difference in face recognition. And then by Nicole Turner Lee from the Brookings Institution, titled Identifying and Evaluating Racial Bias in Face Recognition Technology. And we will close this workshop at in the afternoon with a panel discussion on bias, fairness, and ethics in biometrics. So we have what we consider to be an interesting and exciting program ahead, especially with the three papers and the four keynote talks. So I'd like to welcome each one of you to be involved in the presentations, asking questions, debating and discussing to the extent possible. Let's make it very lively. And I'd like to welcome those who are on Zoom, as well as those who are in beautiful Hawaii. Greetings from here. I'm going to hand this over to Carl so that he can introduce the first talk and then take over the proceedings. So Carl, over to you. Thank you.
All right. Thank you, Arun. Hello. I am Carl Rixenek, and I will be your session chair. I am a faculty member in computer science at the University of North Carolina, Wilmington, and a co-founder of a technology company that focuses on facial analytics, and we deal with the area of bias as well. Today, we're going to have our first talk. Our first talk is going to be on algorithm fairness in face morphing attack detection. And I will start the talk now.
Hello everyone, my name is Raghavendra Ramachandra. I am from Norwegian University of Science and Technology, Norway. So in this work,
let's see, was it displaying to you guys?
It was very briefly. Yeah, there.
Okay, there we go. Sorry. Yeah, is that it?
A little bit over to the left.
Okay.
No, not there. Over.
Yeah. Come on. Oh, I can't seem to hit that. We'll play it and then we'll try to get it full screen.
try to benchmark different face morph attack detection algorithms to study their fairness for different demographic data. So outline of my talk is as follows. So first I will provide a very brief introduction on face recognition. Hello everyone, my name is Raghavendra Ramachandra. I am from Norwegian University of Science and Technology, Norway. So in this work, we try to benchmark different face morph attack detection algorithms to study their fairness for different demographic data. So outline of my talk is as follows. So first I will provide a very brief introduction on face recognition as well as face morph attacks. And then I will give the very brief introduction on the face morph attack detection techniques which are existing today. So then I will provide in details about our newly constructed database, especially within the scope of this work. And we name the database as mixed ethnicity morph dataset. So then I will report several quantitative results that we have designed to give insights on different morph attack detection algorithms and their variation in the detection performance, especially with different demographic data. Based on the obtained results, I will also present several discussions and then we can draw the conclusions. So as we know that the face recognition systems are widely deployed and employed in several types of application. And today the face recognition system has become an integral part of our everyday life. The face recognition system has been used in a very trivial applications such as unlocking the smartphone till the very complex and highly secure applications such as border control systems. So when we consider the face recognition system, especially in the border controls, so there is a recommendation from ECO to use the face biometrics as the primary identifier, especially in the e-passports. So as a result, there are more than 800 million passports which are deployed with face biometrics. So as the face biometric system has become prominent in our everyday life, so attacks on the face recognition system also exponentially increased. So however, there exist several types of attacks. The attacks on the face recognition system that can be broadly classified as direct attack and the indirect attack. Within the scope of the direct attack, so the most prominent type of attack is based on the presentation attack detection, and the other kind of attacks is the face morphing attack. So in case of the face morphing attack, attacker can use two face images. For instance, as you see in this slide, the subject 1 and the subject 2. So then we can perform the morphing operation on the subject 1 and subject 2 to get the morph face image. The interesting thing about this morph face image is it is difficult for both human observer as well as the automatic face recognition system to identify these kind of attacks. This is because if we feed this image to the automatic face recognition system, the automatic face recognition system will verify the morphed face image to both subject 1 and subject 2 in this case. So the face morph generation is a very trivial task. There exist several open source softwares to do that. So as a result, for example, in this slide, I will present a very simple way of generating the face morphing, which is also a very open source. So if we assume that there are two subjects here, one is the malicious actor and the other one is the accomplished. So given the two face images, so we can simply extract the landmarks. Based on the landmarks, we can construct the triangles. And these triangles are wrapped and blended with the certain factors to obtain the morphed image. So when we perform the blending, the factor of the alpha can be varied. So for instance, if you see in this figure here, if we choose alpha as in 30%, then the resulting morphed image is more similar to that of the malicious actor. Similarly, if it is 70%, it is more similar to that of an accomplished. But in case of in the 50%, it is like an average of both face images. In all the three cases, so the morph face images are vulnerable in the automatic face recognition system. That means that if we enroll the morphed face image to the face recognition system, and if we probe both these two face images, for example, the malicious actor as well as in the accomplished, then face recognition system will show that both of these data subjects can be verified against the enrolled subject. So as a result, As a result, this kind of attacks can be used, especially in the passport control. So for an example, there is a real case happened in the Germany. So there is a German activist used a mock face image of Federica. So she is an high representative of European Union for Foreign Affairs and Security Policy. So the activist took a photo with the another photo of the Federica. So and then she performed the face morphing. Then she took that morphed image to the German passport application control, and she was very much successful to obtain the passport. That means that the morphed image presented by the activist, activist was so difficult to be identified by the border control or the application process officer. That means that the vulnerability of this morphed image, even for the humans, are at the very high. So as a result, there exist several face morph attack detection algorithms in the literature. So that can be broadly classified into two types. The first type is the single image based morph attack detection, where the goal is to classify a given single image as in morph or in bona fide. So this kind of techniques are very much useful in case of in the passport application scenario, where the second type of the technique is the differential image-based morph attack detection. So in case of the differential image-based morph attack detection, so there is a luxury of having two images. The one image is from the passport, and the other image is from the border control gates. The image from the automatic border control gates are captured from the live subject who is processing the passport. So if the image in the passport is morphed, then we can devise an algorithm that can use both of these images in a different operations, in different differential operations, to make the final decision on the image in the passport is a morphed image or not. So when we look into the literature, there exist several varieties of morph attack detection algorithms. Even within the single image-based MAD, there are like 5 different types. However, even with the differential image-based MAD, there are like another 5 or 6 different types. So, however, within the scope of this work, we would like to present the analysis on the algorithmic fairness, especially from the single image-based morph attack detection. So why we are looking for the bias in the MAD? Because of the 3 main reasons. The first thing is the all morph attack detection algorithms, especially the single image-based morph attack detection algorithms, are based on the face images. That means that the face images are captured with different environment conditions, face images are from the different ages, they are from the different ethnicity groups, and so on and so forth. And all existing MAD algorithms are based on the learning. They use well-known machine learning-based classifiers. They use deep learning-based classifiers. They also try to use different varieties of the classifier that are basically a data-driven. So since these are all data-driven, it is quite interesting to see and analyze how these algorithms will behave with different demographic data and other variations within the data. And as I already mentioned, another motivation for bias in the MAD is the sensitivity to the various factors. So since the morph attack detection algorithm should work within the same within the same scope or within the same scope of the face recognition system, it is highly sensitive to the aging, gender, and the ethnicity bias. So these factors have motivated us to look for the bias in MAD attack detection. To systematically analyze this, so we put forward 3 research questions. The first research question is, does the ethnicity influence the detection performance of SMAD? And the second research question is, which ethnic group the detection is most challenging, and the third is among the 6 different MAD algorithms that was evaluated, which one is assumed to be more fair or more robust across these ethnic groups. So in order to effectively analyze the data, we come up with the new database, and this database is constructed using several publicly available databases. In this work, we try to analyze 4 different ethnicity. Ethnicity 1 is African, ethnicity 2 is Chinese, ethnicity 3 is Hispanic, and ethnicity 4 is Indian. And the morph image or generated based on the landmark-based method by considering its easiness and the flexibility, and also the vulnerability of such a morph generation is quite high. So in total, the database what we have generated is having roughly around 24,874 images that are spread across 4 different ethnicity, and we also have a clear distinction of training as well as testing images. So this is the example of our face image from the newly constructed database. We see that there is a lot of variations with respect to the each ethnicity group, and we also took additional care to make sure that the images should represent the passport enrollment quality images. Therefore, we make sure that there is not so much variation in the light, expression, and so on. So most of these images will represent a highly constrained conditions. So in order to effectively benchmark different single image based morph attack detection, so we try to choose 3 different categories. The first one is the deep feature based, and the second one is the morphing noise based, and third one is the handcrafted features. So in the first version, the deep feature based, we try to use the existing pre-trained CNN networks, which was proposed by other researchers for the MAD attack detection. So we use 2 pre-trained AlexNet and the ResNet 101, and for the morph noise based method, we use color denoising and the residual noise. And for the handcrafted features, we use ensemble of features and the hybrid features. So these 6 algorithms are very well shown that they perform well on the several databases that have been reported in the literature. So in order to effectively perform the experiments, we have 3 different protocol. The first is the inter-ethnicity, that means that training with the same ethnicity and testing with the same, and the inter, that means that training with one type of ethnicity and testing with another type of ethnicity, and in the third, training all and testing all evaluation. So most of these experimental protocols are designed such that it can give insights on the variation in the performance, especially when different ethnicity is used for training and for the testing. And to benchmark the results, so we try to use ISO-IEC metrics, that is APCR, BPCR, and also we include DE-equal rate. So, and also we particularly use the other kind of fairness metric that is called as FTR, so which is represented as shown in the figure. So based on the obtained results, I am not presenting all results in the total, but the most important observation what we have seen here among all the 6 algorithms is none of these algorithms are robust with the change in the ethnicity. Their performance will degrade to the larger extent when they're trained and tested against the different ethnicity. So this shows that these algorithms are biased too much towards the ethnicity. And once we benchmark the fairness discrepancy rate across different ethnicities here, if there is if the change is less from 10% threshold to 5% threshold of APCR, then the algorithm is said to be a fair algorithm. But as you see here, all the 6 algorithms across different combinations of ethnicity, none of them shows a consistent fairness across different groups. But however, when we consider all 6 algorithms together, we can say that one of the algorithm is good with one combination of ethnicity, and other kind of algorithm is good with another type of combination of the ethnicities. So this again demonstrates that the existing morph attack detection algorithms severely lacks the fairness, especially towards the demographic bias. Well, now based on the obtained results, we try to answer 3 questions. So first question is, does the ethnicity influence the detection performance of SMAD? Based on all the experiments we have obtained, so we see that the algorithms are influenced by the ethnicity of the subjects used for both training as well as the testing. Similarly, for the which ethnicity groups, of course, we cannot accurately say which ethnicity group is more challenging to be detected, because there are several factors will come into picture that also includes the variation in the databases and so on and so forth. But however, almost all the ethnicity groups are quite challenging to detect when the MAD algorithms are trained on one type of ethnicity and tested on other type of ethnicity. So among the 6 different type of MAD algorithms we have tested, we noticed that the use of residual noise-based method is quite robust when compared to the other existing methods. So that means that if we use the residual noise-based method, probably we can achieve a little bit of generalization. But however, this method is also highly vulnerable or shows the degradation, especially when trained and tested against different ethnicity. So with this, I would like to end my talk and thank you very much. If you have any questions, please do contact me via email. Thank you very much.
All right. Thank you. For our audience, either here or on the net, do you have a question? We may have time for just one, possibly two questions. So.
The use of ethnicity is incorrect here. To cultural context, it should really be called race. And this is something that we should converge on. If you look at the definition, the physical, the biological part is race, and the cultural part is we should all use the same terminology. Very nice.
Okay.
I'm wondering whether some of this can be explained, some of the discrepancy can be explained by the number of data points that are used. If you look at ethnicity 1, there's a very large number of test cases compared to the others. And that may actually affect each of the group comparisons, have to control the group sizes as well.
All right. Do we have anyone from this? Oh, we do. Were you able to hear the question? I can restate it for you.
No, I could not hear the question.
Okay, can you come up for the question, please? One moment.
Yeah, so first of all, it's a very nice talk, but I just want to make sure we are all as a community using the same words, and ethnicity relates to the cultural aspects. When you're talking about the biological side of it, it is race. So really what you're measuring here is race, not ethnicity. The other point I wanted to get a clarification on is your data for ethnicity 1 is an order of magnitude larger for the other ethnicity. Can that explain some of the differences in performance?
Yes, exactly. So I noted your first point. So I agree that we might use the race. So for the second question, yes, the database what we have used is not only the sizes are different, but also the environmental conditions in which these different demographic groups are captured is also quite different. So that is one of the challenge why we could not draw exactly what is the variation across inter-race type of experiment, like when we train systems with one type of race and tested against the other. So that is the one kind of limitation of the present work, which is due to the limitation of the databases we have.
All right. All right. Do we have any questions from our great audience on the web? You can put it in the chat if you have a question. So it says, thank you for your insightful presentation. I'm wondering if you could suggest a GAN-based face morphing open source tool.
Yes, so I think from our group, we have published a recent GAN-based open morph tool called MidGAN. So I'm going to post a link to download that code.
All right. Well, thank you for that. And as he posts this link here, we are now going to transition to our first keynote talk. I will invite Dr. King up to do the introductions for this keynote talk. I just need you to get Dr. Frosty.
Welcome, everyone. My name is Michael King, professor in the Department of Computer Engineering and Sciences at Florida Institute of Technology, and here to introduce our first keynote talk entitled Results in Trustworthy Machine Learning, Recent Results in Trustworthy Machine Learning that Go Against Conventional Wisdom by Dr. Kush Varsini, who is a distinguished research staff member and manager with the IBM research team at TJ Watson Research Center. He leads the machine learning group in the Foundations of Trustworthy AI department. He was also been a visiting scientist at IBM Research Africa, Nairobi, Kenya in 2019. He is the founding co-director of the IBM Science for Social Good initiative. He has won several recognitions, including the Harvard Belfer Center Tech Spotlight runner-up for AI Fairness 360. And he's currently writing and self-publishing a book entitled Trustworthy Machine Learning. And he is a senior member of the IEEE. And so without further delay, let us welcome our esteemed first keynote speaker here for his talk in this subject matter. Welcome, Dr. Varsini.
Yep, thank you so much. And just out of curiosity, how many people do we have in the audience?
We have roughly 15 here in the audience.
Awesome, excellent. And yeah, thanks for allowing me to participate virtually. So are you able to see my screen?
Yes.
Yes, awesome, great. So at the end, we heard, so I actually finished writing the book. So that I finished it last week. So it's Trustworthy Machine Learning, and you all can check it out at www.trustworthymachinelearning.com. And I'm going to be creating a paperback version and putting it up on Amazon in the next few weeks, but it's completely free as a PDF. So please feel free to go and look at that. Right? All right, so the talk is about kind of results that go against conventional wisdom. So let's see if that actually is true or not. Maybe your wisdom is more advanced than mine, so so we'll see, right? And feel free to interrupt at any time. And for folks on the Zoom also, I mean, feel free to write things into the chat or anything that you would want to do. All right. So one thing that I wanted to just kind of get across to begin with is, what do I mean when we say trustworthy machine learning? So machine learning, as I think all of us are well aware, is now being used in all sorts of high-stakes decision-making applications, whether it's credit, whether it's employment, so hiring and firing and promotion decisions, college admissions, grading, in the criminal justice system for pretrial detention decision, sentencing, etc. Okay. And it's very important that we actually trust the machine learning models that are behind some of those decisions. Okay? And just as a side note, the second picture, the employment one, that is a picture of the IBM TJ Watson Research Center where I normally work. Okay. All right, so when I say trustworthiness, there's actually several sort of components to it. Oops, sorry. So it turns out that in the organizational management literature, they've come up with a set of 4 attributes that pretty much correspond to what it means for a human being, for another person to be trustworthy. And that's also kind of what it means for an AI system to be trustworthy. So the first attribute is if the other person is competent at what they're doing, they do what they say they're going to do. Second is that they're reliable, so that competence sticks around in different conditions. Third attribute is some level of openness or intimacy, so you can communicate back and forth with the other person. And the fourth attribute is some level of selflessness, so that the other person is working for something more than just their own goals. Okay, so how do those map to machine learning? So the first attribute relates to predictive performance, like accuracy. Second attribute relates to things like distributional robustness, fairness, adversarial robustness, and so forth. Third attribute is related to things, again, that I said about communicating, right? So interaction, so communicating from the machine to the human. So that includes explainability, uncertainty quantification as well. So can the machine tell you what its own limitations are? Is it humble? There's transparency in terms of the entire pipeline and life cycle. And then the other direction as well. So can we as humans instruct the machine of what we want, what does society want? And that's called value alignment. Okay. And then the fourth attribute relates to using machine learning and AI technologies for social good. And just as importantly, empowering people of all kinds, no matter what their station in life is, to be able to use these technologies for their own goals. Okay. All right, so just to get a little bit more into kind of these topics a little in a different way. So I'm going to use an analogy with processed food, which was a big thing when it was not trustworthy when it first started in the late 1800s. So it was really kind of new and novel at that time that you could buy food that was already made, right? And I'm not a paid spokesperson for the Heinz company, but I think they're a good example, right? So they were one of the few companies at the beginning of processed food who were guaranteeing that they would use unadulterated ingredients in their ketchups and sauces, whereas others were using wood pulp and other fillers. They were the first to offer their ketchup in clear glass transparent containers when others were using dark containers. They were the first to offer free factory tours open to the public and also innovated a lot on sanitary food preparation. They lobbied for the Pure Food and Drug Act of 1905, which eventually led to a lot of labeling requirements, as well as tamper-resistant packaging. And the processed food industry these days is very big on using blockchain for transparency. And part of what the Heinz sort of mission was to let people spend their time doing other things beyond preparing those foods that they could buy, right? So not everything was great at that time, right? So in the late 1800s, early 1900s, there was a tradition called muckraking, in which various activists and journalists would investigate the practices of the food processing industry and reveal all of the bad stuff that was happening, right? And the analogy is true today with AI and machine learning, right? So there was a book a few years ago, Weapons of Math Destruction by Cathy O'Neill, which positions itself as part of that same muckraking tradition. And it talks about all these different examples of AI that have gone bad. Right? Another example is Joy Buolamwini, whose image is shown on the right. So we'll get into some more details of what she did and is continuing to do. All right, so if there's the analogy on the muckraking, the analogy extends to the actual topics as well. So when we're talking about unadulterated ingredients, we're talking about an analogy of data quality. Okay? When we're talking about tamper-resistant packaging, that's adversarial robustness to prevent poisoning and so forth. When we're talking about clear glass containers, that's like interpretable models. When we're talking about factory tours, it's like transparency, and so on and so forth, right? Using having the social mission and things of that sort. Okay, so that's what I mean when I say trustworthy machine learning. And now moving into the actual main part of the talk, right? So some pieces of conventional wisdom that seem to be floating around, right? One is that all computer vision systems yield systematic disadvantage to dark-skinned people. And another piece of conventional wisdom is that there's a trade-off between explainability and accuracy. And a third is that there's a trade-off between fairness and accuracy. Okay, so let me go through these and see kind of what we come up with, and are they the way we really should be thinking about the world, or is there some further nuance to it? And related to the question that was asked in person, I would actually argue against race being a biological construct. So I would call it a social construct as much as ethnicity is, because race is not a biological thing either. So I just wanted to mention that as well. Okay. All right, so starting with the first one, that all computer vision systems yield systematic disadvantage to dark-skinned people. Okay. All right, so this is the first part of the talk is related to dermatology. Okay. All right, so just to get us going, all right, so skin diseases are a big part of the global disease burden, and there are disparities with respect to race. Again, this is a social construct that exists in dermatology. So in Black people, melanoma is diagnosed later and at a more advanced stage. The 5-year survival rate is quite a bit worse among Blacks as well. Okay. And as most of us probably are aware, there's been a lot of recent advances in the computer vision aspects of automated skin image analysis. And it's also true separately that machine learning systems may place certain groups of people at systematic disadvantage due to biases in data sets. Okay. So our research questions were the following. So are the standard dermatology image data sets biased with respect to the skin type? And if so, does the data set bias lead to unequal performance of downstream disease classification? So in terms of related work, so there's this entire set of data sets and challenges called ISIC. And it's been put together over the last several years, and it I think is a great service to the computer vision community. Noel Cadella and many others. And the other sort of related work is that we do know that there are examples of predictive inequity in computer vision with respect to skin type, right? So the gender shades work by Joy Bulamwini and Timnit Gebru is a great example of that. It showed for many commercial face attribute classification algorithms, back in 2017, there was a disparity across dark skinned females versus light skinned males and so forth. There's other examples with pedestrian detection systems and so forth, right? All right. So these standard data sets, so there's two, there's ISIC 2018, there's the SD 198 as well. On the left, the ISIC one is dermoscopic images. So there's a special camera with a special illumination that takes very nice controlled images. And the SD data set is like normal cameras, so optical images that you would take. There's 7 disease classes in this ISIC data set. There's 198 disease classes in the SD198. And some of the ISIC ones do have a segmentation mask for where the diseased area is and where the diseased area is not. All right, so we had to do some data pre-processing on the SD198. We removed classes of images that have no observable non-diseased skin, as well as images that only show either the palms or the soles of the feet or the inside of the mouth, from which it's very difficult to know what the skin tone of the individual is. So that got us down to 136 classes. And since that data set doesn't have any segmentation masks, we manually segmented a subset of them to know where the non-disease skin is compared to the disease skin. Okay. And just to show images that we dropped, so at the top, those are some examples of the manual segmentation that we did as bottom. So the methodology that we wanted to follow is we start with the skin images. There's a segmentation model and there's a skin disease classification model. Both are deep learning methods. We take the skin segmentation, only look at the non-disease skin, estimate the skin tone for the unaffected skin region, and then look at the classification performance disaggregated by the skin tone. Okay? And that's would be our evaluation of the skin tone with respect to, or the classifier performance with respect to the skin tone, right? So the segmentation, I'm not going to go into the details here. It was a mask RCNN that we fine-tuned. Once you do that, you have the non-diseased pixels, and you can compute what's called an individual typology angle, and it's highly correlated with the melanin index and so forth, also highly correlated with the Fitzpatrick scale. So we end up with these different categories, very light all the way to dark. Okay. Again, we're not going to go into the details of the classifier itself so much, but it was a fine-tuned DenseNet that was pre-trained on ImageNet, and et cetera, et cetera. The point being that it was pretty much on par with the state-of-the-art methods when we did the work that were non-ensemble methods. Okay. All right, so in terms of the results, so first of all, the frequency of the skin tone bins in the two data sets, as you probably would have guessed, are very skewed towards the lighter skin. There's very, very little dark-skinned images in both data sets. Okay. But what does that mean? Does that mean that we're also going to have poor disease classification or not? That was our main question. And it turns out that the accuracy of the disease classification by skin tone did not show any statistically significant pattern of unequal performance. Okay, so this is quite an interesting finding. So that normally, I mean, we see that there is bias in the data sets, and it does seem to affect the classification results here. That was not the case, but we also have to take it with somewhat of a grain of salt because there were many fewer dark skin samples, right? So this is one piece of conventional wisdom. It's not always true. It's true many times, but not always. Okay? And now you would ask, but what about face recognition, right? So this is another piece of work. So specifically, we were dealing with the attribute classification task. So just to be clear, we weren't dealing with detection or verification or recognition, but on the gender classification task. Okay. The Bulamwini work with Gebru was extended later by Raji and Bulamwini, and showed continuously, I mean, even after many corporations improved their algorithms, that there was discrepancy and poor performance for dark-skinned females, right? So what we wanted to ask is why? Why is that the case? Is it because of the skin type or not? Okay. So we recreated the results in August 2018 using an approximation to the PPB Parliament's benchmark data set that Bulamwini and Gebru had used. We couldn't use theirs directly because the terms and conditions were not something that IBM was willing to agree to. But these were all public images, so we were able to get almost all of them. The only difference was there was an election between the time we pulled our images and when Bulamwini and Gebru pulled theirs in one of the countries in Africa. So there was a little bit of a difference, but almost the same data set. Okay. And what we observed is very similar to what they observed. The dark-skinned female error rate was 17.5% and much lower for the other three groups. And this was using the IBM Watson face classification API of August 2018. Okay. So if the unequal performance is because of skin tone, then we should be able to get rid of the inequality by making the neural network invariant to skin tone using color theory. That was our starting sort of hypothesis. Okay. So we came up with a couple of schemes using color theory based on either a luminance mode shift or an optimal transport to take an input image and to change the skin tone distribution of that image. We didn't want to use a GAN or any other sort of AI-based technique for doing this because those techniques themselves can have their own biases. So we wanted to do something that was very mathematically like straightforward. Okay. So this is what we did, and the question was, is this going to help us or not? And it turned out that there was actually very little effect from the darkening or the lightening on the performance. So pretty much the classifier kept making the same classifications even when we lightened or darkened the skin tone of all of these images. So this is more of like a causal inference sort of thing because we actually created the counterfactual, and we were able to show to ourselves that it's actually not the skin type that's the reason for these discrepancies. And if you think back to it, we actually had dark-skinned males with a very low error rate as well. So even before we started, we probably should have guessed that maybe it's not the skin tone. Okay. All right, so then we had a second hypothesis. Maybe it's about the length of the hair. So when we looked through the data set, 29 out of the 33 misclassified dark-skinned females had hair that was short in length. Okay. Similarly for the others, right? So the dark-skinned short-haired females had a 25% error rate, whereas the dark-skinned long-haired females had 8%. And even on the light-skinned females, that was same pattern was there. So 10% error on the light-skinned short-haired females and 0.5% error on the light-skinned long-haired females. So our conjecture was maybe the hair length is the problem here. Okay. So what we did was we actually took a classifier that had face images tightly cropped. So it only showed the main part of the face and excluded all the hair. And we continued to have the same unequal class performance across the groups. And so hair length was not the reason directly either. Okay. So lastly, the thing that we tried was to use this contrastive explanations method, which is a post hoc explanation method, which will highlight the superpixels in which the minimum change in order to change the predicted class label. And what we found is that the parts of the image on the females that were getting highlighted were the lips and the eyes and the cheeks a little bit. And this is what we thought was kind of this interesting sort of thing, right? So these were kind of these facial features of the lip makeup, the eye makeup, and the cheek makeup, and so forth, right? So the conclusion in that work was that it wasn't the skin type by itself. And as I said before, the dark skin males and light skin males were actually on par, so we should have probably guessed that before. It wasn't the hair length by itself either, but it's more about the facial features of the red and pink lips, the cheeks, and the eye makeup. And what this corresponds to is stereotypes of celebrities. And as we know, a lot of the commercial algorithms at that time were trained on celebrity images. So what we conjecture is that there's much more of a discrepancy between what normal people look like and celebrities look like among dark-skinned females. So celebrity dark-skinned females are maybe more done up in their photos. Okay. Right. So again, it's not about the skin tone per se. It's more about the social aspects that are coming through. Okay. So continuing on, second piece of conventional wisdom that I wanted to somewhat dispel is that there's a trade-off between explainability and accuracy. Okay. All right, so a lot of you have probably seen this picture from the DARPA XAI program where they have some notional graph that has explainability on one axis and has accuracy on the other axis, and they show that there's some sort of trade-off curve. To me, that's not the right way to look at it, and I'll tell you why. So when we're using these machine learning algorithms, they're often used in a human-machine collaboration sense. So the output of the machine is used as an input for a human decision maker to make their final decision. And when you're creating this human plus AI team, I like this interesting quote: "The hard part isn't the AI, it's not the human, even the human, it's the plus," right? How do they collaborate? So what we wanted to do this analysis as is a communication or a distributed detection problem. What we wanted to do was model the output of the machine learning model as a multi-level quantizer. So there will be two levels or one bit when it's a black box model. So the model is just telling you yes or no, whatever the classification, binary classification is. And if it's an interpretable model, it's providing us more than two levels. Not too many, but more than two levels. And what we wanted to do was analyze the overall accuracy of the human-machine collaboration, not just the machine in isolation. And if we can prove that the system with two levels has larger probability of error, or in other words, the system with more than two levels has better accuracy, then we've shown that there is no trade-off in that way that people conceive of it. So again, we have a binary classification problem with labels Y. There's features X1 that are observed by the machine, and we have features X2 that are observed by the human, and they're independent conditioned on Y. So you can imagine a setting, let's say there's a patient in the ICU, the machine gets access to all the sensors that are attached to the patient, whereas when the doctor walks in, maybe they can see that the patient, just on their face, that they don't look good or their skin is pale or something like that. And then we have U, which is an optimally quantized version of the optimal classification based on X1 to the number of levels, which is K. And then the final prediction is what the human is making, again, optimally, based on the input U coming from the machine and their own local observations X2. Okay. So what we showed in this work is that using this quantity called Chernoff information, which is used as a sort of error exponent in information theory to analyze binary classification problems, that when the number of levels K is, so there's two possibilities. There's levels K and there's level K prime. So K prime is more than K. Then the Chernoff information with K prime is more than the Chernoff information for K. And because of how they relate to the Bayesian probability of error, the Chernoff informations, that means that the probability of error in the two-node network with K equals 2 quantizer levels is larger than the probability of error of the network with K prime greater than 2 quantization levels. So that does show, I mean, what we wanted to show, okay? So this doesn't imply that more quantization levels necessarily lead to more interpretability, just that more than 2 is better from from 2, okay? And this abstraction doesn't differentiate between a truly interpretable model and if you quantize a score function or other things. It does assume this conditional independence. It does assume that you're in the population setting so that you have an infinite amount of data so that all models have the same optimal accuracy and so forth. But it does get us to start thinking about the fact that we don't have to think of explainability and accuracy as trade-offs. Okay. And just to wrap up very quickly, again, there's this question that people have, is there a trade-off between fairness and accuracy, right? We've done a similar sort of Chernoff information-based analysis of fairness and accuracy. The high-level message is that accuracy should be measured with respect to an ideal construct space distribution. So what do I mean by that? Okay. So we should think about a construct space as the world that's kind of like the ideal world where people are who they are. There's no like biases or anything like that. Okay. Then when we measure things, when we decide on features, that can introduce social biases. So there can be features that encode structural biases from society, and because of that, there's unfairness and so forth. And then by sampling, by preparing the data, et cetera, we can have more and more biases. Okay. So when we are working in this construct space, that's where it really makes sense to compute accuracy, because if you're already in a flawed sort of world where there's already biases, and then you're looking at accuracy with respect to biased data, then what does accuracy really mean, right? So if we are in that construct space, both fairness and accuracy can improve simultaneously using some analysis that we did on based on Chernoff information. So let me leave it at that. And happy to take questions, discussion, anything that you guys want. These links at the bottom are a lot of the open source toolkits that my group has created in the last several years for fairness, explainability, privacy, adversarial robustness, causal inference, uncertainty quantification, and fact sheets. So feel free to check those out as well. Right? Great, thanks.
All right. Thank you, Dr. Varshney, for your inspiring and informative talk. We have time for a few questions. We have about 7 minutes, a little longer than actually, around 12 minutes. And I'd like to start with those internal. Would you come up? Yeah.
Hello, Dr. Varshney. I was intrigued by your talk, and very specifically intrigued by a notion that you stated around the first part of your talk, looking at sort of the data set and a celebrity bias. Could you elaborate just a little more on that? And given that we have now moved away from celebrity-based data sets, could you speak to that as well?
Yeah, absolutely. So again, we don't have, I mean, some like a proof for it, but like when Bulamwini and Gabriel did their work, the models were, we think, we know for the Watson one, for the others, we think they were trained mostly on celebrity images, right? And so if there is a discrepancy between what these parliamentarians or like regular people look like and what the training data was, the celebrity images being that's training data, then that's going to be resulting in I mean, loss of accuracy, right? So when celebrities are photographed in public, they're often like have a lot of like really like bright lipstick makeup, female celebrities, I mean, a lot of eye makeup and so forth, right? Potentially the cheek makeup. So that difference between what, like how do the celebrities present themselves versus regular people is what we're keying in on. And it looks like it's much more different among dark-skinned females than it is for any other group. So that was kind of the point that that was coming across. In terms of what happens now that we don't have as much basis on the celebrity images, yeah, I mean, that effect should go down. And actually, one of the reasons I think there was the ability to improve so quickly between 2017 and 2019 for some of the companies that that were highlighted earlier is that they already had, I mean, improved models in the works with broader training data sets. So just by doing that naturally, you would improve the accuracies across all groups. So yeah, I mean, I think those effects keep going down the broader representation that you have.
Yeah. Thank you for that that answer and the details. It did make me think a lot about some of the cultural biases as we start to think about the use of celebrity data, especially on the darker skinned females, because they typically have a certain look.
Exactly.
And that does reinforce some sort of stereotypical bias that we have as a community into our algorithms. So when you brought that up, it was an aha moment for me. Several years late, though.
Sure.
Are there any other questions from the audience or online via the chat?
Yeah, I do have a question, Dr. King, unless there was someone in the room, you can.
No. I think we can hear you just fine in the room as long as everyone else online can hear you as well. We're good. Go ahead. You can proceed with your question, Dr. Ross.
Yeah, Dr. Varshini, thanks for your excellent comments. One of the things that you mentioned, which even Dr. Rixenek was alluding to, is about the constitution of the training set. But what about the constitution of the developers of the technology, any technology?
Yeah.
From your perspective, to what extent does that impact the final product or the final deliverable?
Yeah, that's an excellent question. So yeah, I mean, so first let me answer very briefly in one way, and then I'll answer more fully in a different way. Okay, so the fact that we had the dermatology example, right? I mean, that shows that even if you have uh, some sort of skewed distribution, most of your training set is, let's say, light skin, that doesn't necessarily translate into poorer performance, right? There has to be something else going on. Right, so that's just the short sort of thing. But towards your main question, right? It's who's doing the development, right? So actually, the book that I just finished writing, so chapter 16, I'll refer to that, and it actually refers to a nice piece of work by De Arteaga. Is the first author, Maria De Arteaga. She's a professor at the University of Texas at Austin. And the question in general is, how does the lived experience of the development team affect what's going on, and especially the lived experience of marginalization? Okay. So there's multiple parts of the development life cycle in an AI system. There's the problem specification part. What is it that we're trying to solve? What are our figures of merit? Setting all of those up. Then there's the data preparation, data understanding and data preparation stages. There's the model development, there's the evaluation, and then there's the deployment and monitoring. Right? So the question is, like, why does one think, or where would the lived experience of people who have had marginalization come into this entire life cycle? And it's not the same in all parts of that life cycle. Okay? So there's two things to note. First is uh, based on how humans work and think. So when you have a very homogenous group of people, even so socioculturally very homogenous, they tend to just not stop and think. They'll just agree with each other and keep moving on. Even if they, I mean, even if they have like differing opinions, they'll just like agree with each other and keep going. Okay. But if you have a group where the people are socioculturally different from each other, then it's much more the case where they'll slow down, talk about contentious issues, really discuss them. And this is true even if all of them like have exactly the same knowledge about the topic, right? It's not that they're necessarily coming with different pieces of knowledge. It's just the fact that they're different from each other that they slow down to discuss. Okay, so that's one point. Second point is that uh, people who have had a lot of privileges in their life compared to people who have suffered a lot or vulnerable or have had marginalization. So the people who have been very privileged don't usually have the imagination to understand what are all of those other harms that could possibly be. People who have experienced marginalization, they can understand their own perspective, they can understand other perspectives from other marginalized groups and the privileged perspective much better than the people who have not experienced those marginalizations. So they have what's called an epistemic advantage. It's much easier for someone who has had marginalization to notice problems and issues and stuff like that. Okay. So based on those two facts, in this entire life cycle, where do we need the lived experience? Where is it most helpful? It's most helpful in the beginning, in the problem specification phase. What problem are we solving? Is it a problem that should be solved or not? Are we setting up the metrics appropriately? Things like that. it's important in the data understanding. Are there biases in the data, things of that sort? But it's not as really that important in the modeling stage, right? Because if you give any expert, no matter what their background is, a very clear problem specification, you give them the data and it doesn't have issues, or you've already highlighted those issues for them, everyone will do a good job, right? I mean, no one's trying to do a bad job. So in the middle is where it's less important to have the diversity, or especially the diversity of marginalization. And then at the end, it's again important because on the evaluation side, again, you're trying to look for the harms, looking for the problems. So it's really at the beginning and the end that you need the diversity with the lived experience, and in the middle, not so much. So one analogy to think about is with flying an airplane, right? There's takeoff, there's cruising, and there's landing, right? In the middle, you just put it on autopilot, as much as I know about flying airplanes. At the beginning and at the end, that's where the human's involved, and that's exactly the points where you need the diverse teams.
All right.
Thank you very much.
We have another question inside the room. So,
Hi, Kush. This is Kevin
Hi.
Boyer.
Yep.
I was thinking of your data that was the accuracy rates across skin tones for skin disease.
Correct. Yes. Yes.
But do the actual, it wasn't the same diseases everywhere. So are there easier or harder diseases to diagnose? And is there a correlation of that with skin tone? And how would you pull that out of the data?
Yes. Perfect question. That's exactly the right question to ask. So is there some sort of confounding where the easier to diagnose diseases might be more prevalent in dark-skinned individuals, for example? And the way you would do it, we do have the disease labels, right? So you would also break this out by the different disease types and look at that accuracy. Is there it's basically kind of a Simpson's paradox sort of question. And we ran out of time to do that analysis. I think it's worth doing. I think some people have done it very recently. The students who are working on it finished their internships and so on, but that is exactly what we should do. That's a perfect question.
okay. So we are at precisely 1 minute left, and we'd like to thank you again for your talk, your very informative talk on this particular subject. The other thing that we will ask of you is, if you don't mind, placing a link to your book.
Yeah.
The chat below.
Yep.
And for the audience that is both online and in person, we have another chance to ask deeper questions to Dr. Varshney a little bit later on at around 1:40 Hawaii Standard Time in the panel. And so let's thank Dr. Varshney again. For those who are virtual, if you could just do virtual hand clap, and for those in the room, if you could give them a hand.
Yep. Thank you so much, and I'll see you in a few hours. Yep.
Yes, we look forward to the discussion in a few hours. I have a couple of questions as well, but I'll hold them for the moderated session.
Awesome. Great. Thank you.
Thank you. And with that, that will conclude the first part of our workshop, and we lead into a 15-minute break. And we'd ask if everyone could be back at 10 a.m. Hawaii Standard Time for the next set of talks related to our workshop. Thank you.
I think that's what I'm gonna do.
Okay, it looks like we have resumed recording, and we're going to start. It's 10 o'clock. And we have 2 talks before the lunch break, I think. The organizers competed to see who could get to introduce our next speaker. Nisha Srinivas is head of research. I believe I got the right title. Head of research or chief scientist at TrueFace AI currently. Prior to that, got to dial in my memory here. She was at Oak Ridge Labs, and then at UNC Wilmington, and then at Oak Ridge Labs. and we're going back in time, at University of Notre Dame, where she got her PhD. Now, I remember Nisha as having incredible energy, incredible positive force, and kind of obsessive about details and preparation. I think all of those are great traits that have been good for her as she has gone forward in her career. And so it's great pleasure for me to introduce her. And I believe the title of the talk is Exploring New Dimensions in Face Recognition Bias. Is that right?
Yes.
Okay, so Nisha, I think you should be able to take over the share screen and, okay, I'm gonna need,
Can you see my slides?
I see your slides. Let me hit one button here to put the, to see if I can move the yeah, okay. Yeah, I just want to move the chat stream out from in front of your slides. Okay, you're ready to go.
And you can see my slides, right?
Yes, I can see your slides. It said exploring new dimensions of face recognition bias.
Mhm.
Yeah, got it.
Thank you, Dr. Boyer. As Dr. Boyer mentioned, I'm Nisha Srinivas. I currently lead the research team at TrueFace AI, which is a Pan-GM company. We are a small face recognition company. We develop face recognition algorithms to be deployed under different scenarios. Our main objective is to build efficient, robust, and accurate and fair face recognition algorithms. My talk today is titled Exploring New Dimensions of Face Recognition Bias. Majority of the research that has been done in the face recognition community is basically focused on improving the performance of face recognition for adults. That is for people over 18 years old. However, the question that comes to mind is, how well do these algorithms perform on a different population, such as children? So the focus of my talk is basically to determine if bias exists, if these current FR algorithms show the existence of bias when applied to children. So according to the NIST FRVT report that was released on 10/28/21, the report actually reports or publishes the performance of 308 algorithms on different NIST categories. But however, there are only 51 algorithms that were evaluated against the child exploitation dataset category at NIST. So the table here presents the top 5 ranking algorithms on the child exploitation dataset. So, and the table basically presents the false non-match rates at different false match rates for the different categories. So one of the key observations that we kind of make here is that the performance of existing algorithms on the child exploitation category is of order of magnitude poorer than that or greater than that of the other categories. And another thing to note here is they actually evaluated at a much lower false match rate. So they evaluated a false match rate of 0.1%. So, and then the other thing that I came to know is, according to the latest report that was released in December, one of the things NIST reported there in their change log is they're actually no longer going to be reporting on the child exploitation data set, as they have lost access to this data set. But according to me and some of the researchers in the field, we feel that the performance of the face recognition algorithm on children has to be monitored and has to be improved. And this is primarily to stop child exploitation. But now in the news, they're also kind of talking about testing facial recognition technology on children in schools or in summer camps. And then we have teenagers who use bank accounts and they do mobile banking, and they're using the mobile banking applications, facial recognition technology. So it is really important that we improve the performance of face recognition algorithms on the children data set, and also study the different biases that kind of exist when you apply these algorithms on a child data set. And this is primarily because the children are no longer protected from facial recognition technology. So one of the reasons one of the reasons the performance of face recognition algorithms has not improved for children is primarily because of the lack of data sets, and also because the face is constantly changing from childhood to when you're adulthood. So the number of data sets, publicly available data sets to perform adult face recognition research is close to around 40, with the largest data set consisting of close to 42 million images and 2 million identities. Whereas for that of children, we have like only around 6 data sets, and the maximum number of identities vary between like 3,000 to 745. And then the total number of images in the largest data set is around 7,919. So below in this table here, I kind of list out the different longitudinal child data sets that are available in research. The one that I've primarily worked with is called In the Wild Child Celebrity Data Set. And basically, we use this data set to study if age, gender, or population bias exists. So the In the Wild Child Celebrity Data Set is basically made up of celebrity children. It's a longitudinal face data set. It consists of age and gender labels. They're kind of wild in nature, so there's a lot of variation in lighting, pose, occlusions, etc. So this data set consists of around 8,000 images with kind of like an equal distribution of males and females. So there are 396 males and there are around 349 females, resulting in a total of 745 subjects. So we are aware that current face recognition algorithms exhibit bias. They exhibit demographic bias. That is the accuracy of face recognition algorithms vary from one demographic group to another. So the performance of the algorithms is different for different ages, across different genders and race. So another thing that current face recognition algorithms exhibit is population bias. So that is, the performance is very different across adults and children. So in some of my earlier work, I had actually evaluated the performance of 8 face recognition algorithms. So this is a mixture of commercial algorithms, government algorithms, and academic algorithms that are all part of like the NIST FRVT. And basically what I wanted to do was to determine if there is an existence of bias in these algorithms when they're applied to children. So I designed 3 experimental setups here to measure each of these biases. So when you compare the performance across experimental setup 1 and experimental setup 2, we kind of are measuring population bias. When we compare the performance of experiment 2 and experimental setup 3, we basically are measuring age bias, and then we solely use experimental 3 to kind of study gender bias. So in experimental setup 1, it's basically made up of an adult face data set. So I've used just the popular labeled faces in the wild data set. So here, how do I construct my target and gallery, or the target and query set? My target is just kind of the first image of the subject in LFW for that particular subject, and then the query set is made up of the remaining images of the subject. Whereas for experimental 2, I call it the youngest versus older setup. Here, if you have multiple images of a subject at different ages, what we do is we enroll. So we enroll the youngest image of the subject we set the youngest image of the subject as the target set, and then the remaining images at different ages are passed into the query set. Whereas for experimental 3, I call it the youngest versus oldest setup. So here, the target image is basically the image of the subject at the youngest age that's available in the data set. And then the query image is one at the maximum age that we have of this subject. So as we perform these experiments, for the first one, the results is population bias. Here I'm comparing the performance across experiments setup 1 and experiment setup 2. So basically the performance of the algorithms on an adult data set and a child data set. And so basically compared across 8 algorithms. So I'm highlighting for one algorithm here on the side. And as we can see, there is a larger overlap between the match scores and non-match scores for the particular algorithm when evaluated against the child data set than the adult data set, indicating that it's going to perform more poorly on the child data set than on the adult data set. So this basically is showing a negative bias towards a child data set. And this kind of phenomena is observed across all the algorithms. All the algorithms perform much better on the adult data set than on child data set. So similarly, I have results here for where we tested the algorithms under a verification scenario, which is a 1:1 scenario where we're basically claiming is so basically the idea is the person who he claims to be. So again, across all algorithms here, if you look at the ROC curve on the right-hand side with the x-axis shows the false accept rate and the y-axis is the true accept rate, we can see that it performs much better on the adult data set than on the child data set. This phenomena is observed across all algorithms. And a similar scenario, similar phenomenon is observed when in the identification scenario where we're performing a 1:n search, and this is kind of like a CMC curve. And here you can see the rank 1 accuracy on the x-axis and the y-axis, the retrieval rate. And we notice that that all the algorithms perform better on adults than on children. So this indicates that current face recognition technology does not work well on children, and it should not be applied to children because they're exhibiting some kind of like population bias here. So the next set of results that I present is for age bias, where I'm comparing the performance across experiments set up 2 and 3. So this is against the youngest versus older, and then the youngest versus oldest setup. So again, under both the verification and the identification scenario, we see there is a degradation in performance in experimental setup 3. So this is primarily because the age difference between the target image and the query set, or the query image, is much larger when compared to the ones in experimental setup 2. Because in experimental setup 2, you have a larger variation in range. There's large age variation in range. So you can, so it's showing a better performance there. So this kind of indicates that there is an age bias that is exhibited by the algorithms when applied to a child data set. And then for gender bias, again, here we observe that all algorithms perform better on females than on males, I think except like one algorithm here. But this is contradictory to what we see in adult face recognition. So in adult face recognition, we've always seen face recognition algorithms that perform better on males than females. So, and then the argument there is because females wear a lot of makeup and they have a lot more changes to their appearance, external appearance, and that's what's kind of contributing to it. But here we see the reverse, we're observing the reverse phenomena where the algorithms are performing better on females than on males. And a similar trend is observed under the identification scenario too. One of the things that we wanted to kind of highlight in this study is, let's say, so basically when we're trying to compare a gallery, I would say, of males and females, and then you have a probe set of just say like males. So which is kind of like the male study. There are two types of errors, the two types of false matches that can occur. So basically male subject is matched to another male subject, or a male subject can be matched to a female subject. And similarly, in kind of like a female study where you're comparing female, the probe set is just made up of your female subjects and your gallery is made up of both males and females. There are again two types of errors that can occur. So that is a female subject can be matched to another female subject, whereas, or a female subject is matched to a male subject. The two errors that are of importance to us here is, how is that a male subject is matched to a female subject? Like, how do they look? Like, how do they look? Or when a female subject is matched to the male subject, like, why does that happen is the questions. So what we noticed here is, so when you compare the false matches across all the algorithms, it looks like more females were being matched to males. So basically when the gallery was made, when the probe was made up of females, they tend to like get matched more to males. And this indicates that the females kind of exhibited more lamb-like behaviors. That is, they had similar characteristics of other subjects within our data set. And then I kind of went and looked at some of the examples of like why this was happening. And one of the things that I noticed was because males and females, as you're growing, right, like we mature at different rates and at different ages. So a lot of the males, when they're in their teens, kind of have a lot of feminine characteristics. So that's why a lot of females were kind of getting matched to the males. So it's basically because of this, because of different maturation times and the way the face develops for males and females is different. So a lot of females were getting matched to kind of the males. So that's kind of like these mismatches are happening. And here from the examples, you can pretty much see a lot of them are very similar. So the main question is, what causes bias in child face recognition, right? So bias in adult face recognition is primarily caused due to the soft tissue changes of the underlying facial skeletal structure, or the underlying facial skeletal structure does not change much because it's fully developed in adults. So it's only the soft tissue changes that kind of happen, and that's, or changes in skin tone and things like that. So whereas for child face recognition, the bias primarily exists due to the difference in growth velocity, the development and maturation of the underlying craniofacial structure or the facial skeleton of the face. So, and this is also very different for males and females across different populations. So one of the things that while we're growing up, especially when from your zero to when you hit like that maturation point, right, is our face shape is constantly changing. And there's actually like a sequential growth in our face. So initially we kind of have this, our forehead's kind of bigger. Then as we kind of age, you know, we're developing our face, so it kind of gets broader, and then our face depth increases. And then finally there's like an increase in facial height. Like, you know, that's how the growth pattern is for a face. That's how a face is developing. And as we're getting older, the child's face will kind of flatten, it'll become more deep, wide, and lengthen, and will start kind of having that adult appearance. So the face is like constantly changing. There's very little like soft tissue changes, but there's a lot of craniofacial changes that are happening. So I'm gonna, in the next few slides, kind of highlight the different components of the face and the velocities at which they're growing. So some of the regions that I'm going to focus on is kind of the orbital region, that's the eye region, the nasal region, the nose, the maxilla region, that's kind of like the cheeks, and then the mandible region, which is kind of the jaw and the mouth. So they're all growing at different rates. So here I actually have a diagram of how the sequential growth of a face happens over time, you know, from childhood to adolescence, like, or when you're like an adult. So as you can see here, especially when you look at the table on the right-hand side, you can see how the cranial volume changes at different points of time. You can see the ratio between the cranial volume and then the facial volume. So one of the things that also makes child face recognition very hard is these reasons, right? The underlying face structure is constantly changing. So we really need to understand the underlying change to be able to develop better face recognition algorithms. So in the next few slides, I'm going to kind of again go over the types of changes, the nature of changes, and then the timing of the changes that occurs for each of these individual growth. So each component of the face is constantly growing at different rates. Some have rapid growth spurts, and whereas some components they'll grow at like a steady passive pace till we reach, and this is till we reach like that maturation point or like that full adult appearance. So here I'm going to focus on, the first is kind of the orbital region. So the orbital region has 4 different components. And as you can see in each of the tables, I kind of highlight the percentage of adult size it reaches at different points of time in life. So, and it's also very different for males and females. So like, for example, for the orbital height, like it's developed 78% of the adult size by the time we're around 5 years old. And there's only a 10% growth change in the next 2 years. Okay, and then by around 10.5 years or like around 11 years old, so females have already developed 98% of it, whereas males have developed only 91.5% of it. Right? And similarly again, so the orbital region seems to be developed really young, very young in our life. So it actually reaches its full maturation by the time we are like 10 years old. Whereas it is a little different for, I can't see the slide, for the nasal bone here. Okay, I can see the slide there. I can see the numbers there, but it's a little different. And then here with the maximal maxilla region, what I can see is there's actually rapid growth between 5 to 11 years old. And then otherwise there's just kind of like a passive growth. And one of the things to note here is for each region, the maturation point for females is different than that of males. And this also kind of causes, it's only later on after like around 14 or 15 years old is when boys really kind of like get their masculine features. And that's kind of the reason is because of this, the changes in the underlying facial structure happen later as they mature later in life. And similarly, the mandible region, I think we reach around 90% of the development by the time we're 15 years old. So in summary, what I would like to say is the underlying craniofacial structure is constantly changing from birth to maturation, which makes identifying children very hard. So it's a very challenging problem for child face recognition. And there's also the lack of data sets also contribute to this problem. So in order for us to build efficient, fair face recognition algorithms for children, we really need to understand the growth velocities and the peak growth spurts. So in that way, maybe we can do like some kind of attention guided learning of features while we're building these algorithms. And of course, all of these algorithms, like how we have demographic bias that is exhibited in adults, the same thing is kind of seen in children. And it is very important, like we focus on developing efficient, robust, accurate algorithms for children, and even like fair algorithms, right? Because the children are no longer protected, especially because of social media, there's images easily available everywhere. So they are now being used by companies and people are performing facial recognition technology on them. So we want to make sure, especially children really don't have a voice when they get stuck in trouble. So we want to make sure that we develop fair algorithms for them. So with that, that's my talk. So I'll take any questions.
So Nisha, are you there?
Yeah. So can you see me?
We can go back to seeing you, or we can go back to the slides because I'm going to ask you about slide 13 in just a second. I'm going to exercise prerogative and give you 2 questions real quick. Is the data set that you have participated in collecting available to the world in general?
Yes, so the iTwig data set is available. That's the only publicly available data set that you can download. And Carl is in charge of it.
Okay, can you put a link to it in the chat stream? Because I'm guessing that I'd be surprised if nobody in the audience here and online would be interested in it. So maybe put a link to that, or a link to a paper that makes it clear how to get that or something.
Okay.
Okay, now slide 13. You claimed that this slide showed that females have better accuracy than males. Is that right?
Yes, except there are 2 algorithms that
walk us through it, how you get to that conclusion from this data.
Oh, how they're working better on females than on males?
Yeah, because I mean, I see lines that cross. I see
So majority, the thing is majority of the algorithms perform better. So one of the, hold on. So there is one algorithm.
What do the very best algorithms do?
The very best algorithm is F. That's the best algorithms, and that performs better on females than males, right? So there are a couple of algorithms where the failure to enroll rate is very high, right? And that was mainly because of the male subjects. So it failed to enroll a lot more male or female subjects. So that's why some algorithms show better on males than females. But under the identification scenario,
Okay.
yeah, or maybe I got it mixed up. They actually perform better on males than females.
This is the identification scenario, right?
Yeah.
But you could pick algorithm E, which has very similar performance, right?
Yeah, they have very similar performance. Even F has very similar
It has
performance.
very similar performance. Okay.
Yeah,
And most of the others, all the others have a blue line above the red line.
yeah.
Okay.
I got it mixed up. Sorry. Yeah.
Okay. I'm sorry. I'll stop monopolizing. Questions at large from the room or online? We have a question coming up.
So, Nisha, you spoke about the development of these algorithms. It is a protective class, but there is a large use case for child-based algorithms that are coming in emerging countries, where they're actually tracking these children for things like resources and whatnot. So this is not necessarily a question, but just a call to action that not only are we seeing an increase in face recognition, but we're seeing a large increase in facial analytics with the use of these algorithms to help protect the young ones from in social media context as well. And there have been some really horrific news within certain social media footprints about the misuse or abuse of children on these particular platforms. And in some cases, there have been cases where the children should not have had access because they were too young. And so we're starting to see that, and we're starting to also see governments around the world put some laws in place to hold these social media companies accountable. And they're also putting regulations in place around child face recognition, child analytics, the ability to do this verification as well for age and identity. So this is more of a call to action than anything else. And you guys can reach out if you want the iTwit data set. We have lots of data, far more than what was presented here.
Gerard, question? Oh, I'm sorry. Two people raised hand.
Pat, go ahead.
Go ahead.
Great. Very interesting work, Nisha, and it's great to see you, by the way. I'd like to pile on a little bit to what Carl noted, but at the other end of the age spectrum, face recognition for the elderly people is a topic that badly deserves some focus and some attention because of the concerns of diminished capacity, the fact that elderly people tend to have more money that could be accessed through online services, and B, are likely to have or may have less in the way of family members available for protection from criminal activity. So I'm wondering, from your industrial perspective, or even from your prior work with Carl's group, whether the topic is starting to get attention within the industrial community or the research community.
In the industrial community, I still haven't seen any buzz on it. But I feel like every time we kind of, even when we just do simple age estimation algorithms, like if you want to like create a product just for age estimation, right? Just due to the lack of data set in that particular age range, we're not able to do much work. So, and it's also like very difficult for us right now to collect data. So we don't have the capability, at least like at where I'm working, for us to like collect that kind of data, because their interest is something else. So I feel like it's the lack of data set that's not, because of which we're not able to like do more work in that area. But I do see where you're coming from. But I also think like child face recognition is hard. Like adult face recognition is getting easier now. But I feel like the older generation, because there's like a lot of soft tissue changes, and also I feel like the cranial structure is also changing. So there are two things now that we really haven't like kind of looked into and how they work together to see what the changes are. So I feel like that's going to be a little bit much more harder problem to solve. If we had the right data, we could do it.
That's why it's research. Thank you.
Arun, do you have a question?
Yeah, if you don't mind, a quick question. Nisha, thanks for your talk. And you talked a little bit about the biological and morphological changes that occur on the skull. To what extent can this phenomena be incorporated in face recognition algorithms? I think it was a very good description, but when we especially match age-separated, time-elapsed images, how can we better exploit this model?
So the way that I was thinking, if I had to perform more research related to in this particular area, and if I had the right data set. So if I had, actually there's this data set by the Australian government, right, which has close to like 4 million images and things like that. So then there are multiple images. And I think here for each subject, they have like around 12 to 13 images at different age ranges. So probably what I would kind of do was I would kind of really understand how each region of the face is kind of changing. And when you're trying to perform age variation comparisons, maybe you can do some kind of guided attention. So if there's too much change in the orbital region, you probably don't want your recognition algorithm to focus in that particular region for a particular age range, right? So you want to maybe focus your network to learn from other parts of the face, which are more growing at like a steady pace. So maybe using some kind of guided attention mechanism that way is what I am thinking. So you don't do holistic face recognition here. You don't learn the features holistically. Maybe you do like a region-based learning of features and somehow, and see if you can correlate it to these changes that are happening in the underlying structure. Does that?
Yeah, thank you. And a very quick follow-up thing, which means algorithms that are estimating the age of the face may not be too misplaced, because they can potentially be used for the purposes that you just indicated.
Yes, but I think for this is when you're talking in terms for adults, right? Like the facial structure, the underlying face structure already is very developed.
Right.
It's not changing much. So it's only going to change maybe like Dr. Flynn was saying, after like you're 50, 60 or something, maybe that's when, you know, you start shrinking, your bone starts shrinking and things like that. That's when you kind of observe that change. But otherwise, from the time like maybe you're 18 to like maybe 50, like there's a large point of time where it's constant. The underlying structure is constant, but your skin tone, your soft tissues are constantly changing. And then you being exposed to the environment also is changing your facial texture, right? Skin texture and things like that. I think those are what's contributing more.
Thank you.
So Nisha, I really want to thank you for ending up on all these pleasant things about the changes in the facial structure of people over age, a certain age.
You look the same.
We've heard enough from you. Thank you. Thanks, Nisha.
So with that, we're now ready for our next talk. And this is a keynote on finding causes of demographic accuracy difference in face recognition by Dr. Kevin Boyer, who's a Shumel Prime family endowed professor at the University of Notre Dame in the Department of computer science and engineering. He's a fellow of the American Association for Advancement of Science and also of the IEEE and the International Association of Pattern Recognition. I've had the pleasure and honor of working with Dr. Boyer on this specific topic. I mean, over 20 years now, probably in total, but on this specific topic since about 2018 or so, as a visiting professor, luring him out of the cold of Indiana to the warmth of Florida for a semester. And so I really appreciate that. And so we're really happy to have him to share his insights that he's been working on and covering for the last couple of years. And he too will be a member of the panel a little bit later on. So without further delay, let me welcome Dr. Kevin Boyer to the platform.
Carl. Go out and back in.
Yes, and we're going to do share screen. Share. And we're going to bring your presentation up. There you go, sir.
Is that it?
Yes, sir.
Great. Good, good. Okay, so this is meant to be a discussion presentation rather than a presentation. And I want to look at what
Kevin?
yes.
Sorry for interrupting. We see the presenters view on our side. That's okay, but I just wanted to mention that to you.
Okay, hold on.
We will take
We
care of
don't
that.
see that here. Okay.
Yeah, no worries. We're gonna just swap it.
That better?
Yeah, it looks good now. Thank you so much, and sorry for interrupting.
No, that's good.
All right.
And actually, I'm going to request everyone to interrupt me as often as you like during this talk. Okay. So this talk is looking for causes, but also thinking about what we want as a result of our research, how we talk about it, and what we allow ourselves to look at as causes of research. And so nothing here nothing I'm going to say about any when I say our results or my results. They weren't all done, none of them almost were done by me. They were done by the collaborative efforts of a team at Notre Dame and at FIT. And those are some of the papers, and I will talk about some of the results later will be around this top paper. But I want to go through a couple of things before I get there. Media commentary, I'm going to blow right over because we've all seen that a bunch of times. I'm going to ask you a question about what is the goal of doing something about unequal accuracy. I'm going to ask you a question about, well, how do you really interpret this history of face recognition results? And then we're going to go into, what are the actual differences? Does high accuracy make relative problem size less important? And talk about some speculated and known causes. And this is echoing some of the things in Kush's talk. There was a lot of news headlines about face recognition being biased, face recognition being wrong, and specifically asserting that darker skin tone is associated with higher errors. And it was not only it was in good places as well as questionable. So this is a BBC sort of item. This is a New York Times kind of item, making that explicit thing. And I'm guessing the reporters didn't mean for that part of their article to be pulled out and them to be pinned down to it. They were probably using skin tone as a stand-in for race or something like that.
Now we're seeing your view.
What are you seeing online, Arun?
I think
We are seeing it says the New York Times.
Okay.
And there's an article, and we see some.
But you're seeing a presentation view, right?
That's right. Oh yeah, we are seeing the right presentation view here.
Okay, where's the mouse?
Right there.
Yeah, let's try that. Ha.
Are you still seeing presentation view, Arun?
Yes, we are seeing the same presentation.
Okay, and then a bunch of articles about the racist and sexist history behind face recognition. And my favorite, in a negative sense, example of news coverage, NIST study confirms that facial recognition is a racist, sexist dumpster fire. I'm sure that's not how Patrick Grother wanted that report to be interpreted. And to some degrees, these over sensationalized things are basically the result of the current internet economy, where people need clicks on titles in order to monetize. And so they've given in to that kind of thing. Now, the base problem is that we have observed that for face recognition on two different demographic groups exhibits a different level of accuracy. And here I've put a blue bar with 85% and a red bar with 75%. And maybe that's suggestive of higher accuracy for men than women in face recognition. The question is, what would count as a successful fix? And you're going to say, well, I want equal accuracy. Well, okay, but even if you want equal accuracy, how do you want your equal accuracy, right? Would a successful fix give you equal accuracy where both of the groups now get 70%? Is that, I mean, that's equal accuracy, right? Would it be that you've gone in, and I should say, before I leave that last one, there are examples of this in the literature. The paper's written, here's a new algorithm. I get almost equal accuracy, but it's lower accuracy for all the groups involved, right? Okay, so that's a possibility that's being surfaced by our community, right? Is the goal to look really, really hard, understand things that you didn't understand before, and come up with an algorithm which maybe gives equal accuracy, but slightly better accuracy than any group was getting before, because you now know more, right? And you can just make better algorithms because you know more. Is it an allowable goal to say, well, okay, I'm going to have a new algorithm that makes the accuracy equal, and the way I'm going to do it is whoever had the high accuracy is going to have the low accuracy, right? That's probably pretty achievable from some simple algorithmic sorts of things. Is equal accuracy where you bring the lowest group up to the highest group in order to make them equal? Is that a better kind of accuracy? A better kind of equal accuracy, or the kind of the meet in the middle? I trade off, one group is going to have higher accuracy than it used to, the other group is going to have lower accuracy, but somehow I'm trading one for the other, and that's maybe the more stereotypical way we might think about that. So there's at least these 5 ways of thinking about what it means to achieve equal accuracy. So when someone says, oh, I want equal accuracy, I want to argue that that's not sufficient, that we ought to have an aspiration for what kind of equal accuracy, or what path to equal accuracy. And so for you, are all of these 5 scenarios of equal accuracy just as successful as the others? Does anybody want to advocate that they're all equally successful solutions? How about, I'll call on the audience. Which one's the best for you?
Well, I think the equal and higher is the best. I think that's the toughest one to get, right?
Okay. Okay. So the best solution, is 2 here, equal and higher. I want to somehow have figured out enough about the solution. What's the next best equal accuracy? Yeah, I want to take the lower person and raise them up to high. And I would even say that the equal and lower than you could have either gotten before, I don't consider that an acceptable solution for equal accuracy. You're penalizing both groups by being focused, hyper-focused on wanting their accuracies to be equal. And I don't know that that's a reasonable solution. So one thing I think we're not doing is saying where we want to go in terms of equalized accuracy, and what solutions are acceptable and what are just over focused on a property that's hurting to the extent that you're willing to hurt everybody involved, everybody served by the technology in order to achieve some conceptual goal. Okay. Next, I want to do a brief, I'm calling it history of face recognition. It's not exactly that, but it is a little bit. So this is a picture from Takeo Kanade's early 1970s PhD dissertation. Takeo Kanade, director of the Robotics Institute at CMU for most of my professional career, huge talent in the field. He did face recognition, automatic face recognition for his PhD in the 1970s. Nobody talked about demographic differences in accuracy in face recognition. Probably the next big thing that happened in face recognition, at least in to the degree that I'm aware of it, was eigenfaces, which was a CVPR paper in Hawaii. In fact, let me pause for a moment and enjoy those memories. Yeah, that was I remember that paper being presented. So eigenfaces kind of gave a burst of life to the field of face recognition. So the first 20 years, it was kind of people were doing it, but I'm not sure how big of a field it was. After this paper came out, this work came out, there were eigen irises, eigen gait, eigen everything, right, for a period of time. And still, we're not talking at all about differences in accuracy for different demographic groups. If we come to 2000, early 2000s, so we're 30 years into the history of face recognition. We have an early face recognition vendor test. You see familiar names there, Jonathan Phillips, Patrick Rother, and others at NIST. And this report has a line where it says FRVT 2002 for the first time examined the effects of demographics on performance. So that means we've got maybe a 20-year history of considering this issue at all, right? They said two major effects were found. First, recognition rates for males were higher than for females. And for the top systems, they give some stuff there. And then I think people saw that and paid some attention to it. There were a few papers about accuracy for a while, but the next paper that maybe it didn't make this splash at the time it was published, but it has been referenced an awful lot by detractors as well as researchers in the more recent years, is this one, Face Recognition Performance Role of Demographic Information by Brendan Clare, Mark Burge, and others. And this is a plot from there where it shows that that male ROC curve above the female ROC curve for all of the commercial algorithms and for the research algorithms. And even down at the bottom here, if you train on females, train on males, or train on all and evaluate on males and females, you don't see the difference when you train all. You don't see the difference when you're evaluating only on males or when you're evaluating only on females, regardless of how you train, that you see up here for the different algorithms being evaluated on the data. And this was their only trainable algorithm, and trainable in the old pattern recognition sense, not in the new deep learning sense, right? The thing that I found really interesting when I went back and looked at this paper is the bottom half of this figure, where they actually showed that the imposter distribution for women is worse than the imposter distribution for men, and the genuine distribution for women is worse than the genuine distribution for men. So they had that result in a figure in their paper at that time. And this is an evaluation of a bunch of different algorithms. The FRVT is an evaluation of, the earlier FRVT is an evaluation of a bunch of different algorithms. And then more recently, this is, I think, the report that headline about the racist, sexist dumpster fire was actually referring to. So another 10 years forward, now we're to very recent history, demographic effects. We found that false positives to be 2 to 5 times higher in women than men, with the multiple varying depending on the data set. They're saying country, algorithm, origin, and age. And I guess, I think the data set quality is changing also, I'm going to argue. If not explicitly here, then later I'm going to argue that the content of the data set is changing. And in domestic mugshots, false negatives are higher in Asian and American Indians, with error rates above those in white and black. The lowest false negative rates occur in black faces. The result might not be related to race. Okay. Analyze cause and effect. And this plays into the title of the talk. The NIST study had huge amounts of data, access to lots of algorithms, and could show consistent trends across lots of data from different places across a number of algorithms. So this is kind of the super demonstration of the thing that we had seen 10 years before and that we had seen 10 years before, but just made bigger and current on large amounts of data and large amounts of current algorithms. But nothing about cause and effect, nothing about why we see this effect, nothing about the cause of the effect we see. So here's my question to you. We have studies done around 2000, so 30 years into face recognition history. The first one saying, hey, men and women have different accuracy. And 10 years later, we have something saying, hey, men and women have different accuracy. And if you look in detail, women actually suffer both on the imposter and the genuine distribution, and different races have different accuracy. So that's 40 years in. And very, very recently with the big NIST report, we have 50 years in, so 20 years of history of looking at demographics, another whole set of algorithms that have been evaluated. So in each of these papers, there's multiple state-of-the-art algorithms. They're different data sets, and they're getting larger and more diverse. And there's different researchers behind, different lead researchers behind all of these, right? But different research groups. So what, if anything, does the history of observing demographic differences in face recognition accuracy tell us about the likelihood of different factors being the cause of the difference in accuracy? That's the question. What, if anything, does this sort of look at the history of observations tell us? And here's some possibilities. That algorithm designers have implicit bias in them. We all have, everybody has implicit bias in some sense. And most of the algorithm designers are white males, probably. Or most of the test evaluation people. Are the algorithms themselves biased? Now remember, we have algorithms at 3 different places in history, right? We have the old algorithms. We have some eigenface algorithms. We have commercial algorithms. We have research algorithms where you know the code. You can read the code. Are the algorithms themselves biased? Could we say that eigenfaces, that principal component analysis, biased for or against a demographic group? Is that an allowable thing to say, right? Does it make sense to say that? Are the development data sets biased? Are the demographic groups that are in the data sets, do they, for cultural or social reasons, have different quality of content about their face, image content about their face in their images as groups, right? Or something else? So my question to you, maybe I'll take the Gerard side of the room this time. Does the history of what we've seen, does it favor any of these as possible explanations? You think data sets, or that you should be looking more at the data? Yeah, going through it more. Okay. Any other questions, comments? No? The actual effects that we see that we want to talk about for African Americans, this is out of the Morph data set with the ARC face matcher. We're seeing higher false match rate and higher false non-match rate for women than for men. In Caucasians or African Americans, we're seeing higher false match for women and lower false non-match for women in either, did I do that right? We're seeing higher false match rate and lower false non-match rate for African-American women over Caucasian women, and the same for African-American males over Caucasian males. So those are the general trends. This is our results, but it's the same thing that you would see if you went through the NIST report. This is the general trend in the NIST report. The D primes, the separability of those curves. So D prime is a number which sort of assumes that that all these curves are Gaussian, and it's the mean and the standard deviation, and it talks about the distance. So it's a number which gives us the inherent ability to separate imposter pairs from genuine pairs. For African-American males in the data I just showed you, the D prime is 9.8, really high. For Caucasian males, it's 8.9. For African-American females, it's 8.3. And for Caucasian females, it's 8.2. In some studies, I think we've seen these two flip for different versions of matchers and for smaller versions of this data set in the past. But the fundamental thing here is that for African-American males, the technology overall actually allows for amazing accuracy, right? Depending on how it's used, right? So is this the reference point for choosing all the thresholds? Then you would have the best accuracy for that. You should have the best accuracy for that group. There's a paper that's out, I'm not sure where it's shown up, talking about what did the experts say with respect to demographic fairness in biometric systems. And I want to play with one thought here. And the thought is, does a reduction in error rates, because it decreases the absolute number of different outcomes, improve fairness? In other words, can you decrease the importance of fairness by increasing absolute accuracy? In other words, two cases. Demographic A is 99% accurate. Demographic B is 96% accurate. Another case, demographic A is 90% accurate and demographic B is 60% accurate. Is the bias the same in these two cases? Does one exhibit worse bias than the other?
Yes.
You would argue yes or no?
Yes.
Which one is worse?
From my perspective, it would be case two. I assume case one could be statistically not significant.
No, I'm not going. I did this on a bazillion images.
Okay.
These are the numbers. These are population numbers, right? Is the bias? Do we all? How many people feel that the bias is worse in case two? Raise your hand. I'm seeing 90% of the hands. This is a made-up case. So this is not a real case. I'm trying to get. Can we improve accuracy of the technology so much that this problem goes away? Now, I've chosen these numbers intentionally, right? The fraction, the X of errors for demographic B is the same, right? Right, there's 1% error or 10% error. There's 4 times the error rate for B in either case, right? So the multiple of errors experienced by one group relative to another is the same. I was a little bit surprised that you're all seeming to let the technology. So if we just wait a couple of years, face recognition gets a little bit higher. Are we going to be off the hook for this problem? I don't think the headlines about racist, sexist, dumpster fire are going to disappear if we put one more 9 in the sequence of accuracies, right? I don't think the public attention is going to disappear. The practical impact of how often somebody is inconvenienced and wants redress through the system may change, but I don't know about that. Okay. Speculated and known causes. Things that we've looked at, people have suggested to us and we've looked at: facial expression, Women make a greater variety of facial expressions than men do using facial expression recognition tools on the data sets available to us. That generalism seems to be true. It doesn't seem to account for the recognition accuracy difference. Head pose pitch. For a lot of the types of images we look at in morph, women, the camera's looking down at women a little more than at men. That seems to be true for the pose estimation tools and data set that we have. There's more forehead occlusion by hair. That seems to be true. It's more frequent or a larger amount of it on average. And there's more makeup being worn by women. All those seem to be true. None of those seem to be driving the accuracy difference in the data sets we're looking at. Though certainly you could create a data set where any one of these made an observable accuracy difference. This is a really complicated sort of, so this is a heat map for female. This is female, this is male. This is the difference between male and female. This is a heat map for skin. This is the heat map for hair, right? So this is the heat map for skin. This is the heat map for hair. And you can see from the hot region here and the hot region here, the difference in stereotypical hairstyle between men and women. And you can see that all of the side parts of the image typically have hair much more frequently for women than for men. And that the skin is much more frequent out here for men than for women. And if we look down here, we can see the skin ratio. If you take the 224 by 224 image and you segment it and you find the regions of the face that should represent skin, and you look at those as a fraction of the 224 by 224, you can see that it runs between 20 and 60, but men have a lot more images with a higher fraction of the image representing pixels on the face, so to speak, right? And that's true for African American, and that's true in Asian celeb for some Asian images. This being an in the wild data set, and give us some allowance for a lot of approximations in how to prepare that data for analysis. So when we've observed the result that males have better accuracy in face recognition than females, we have observed it by processing images where males had a higher fraction of the image with pixels on the face than women. Did that make sense? You could maybe even refer to that as a bias of sorts in the test data, in the evaluation data, because not as much on average of the women's face is visible in the image as the men's face. With me? Okay, if we balance, so that we've switched now to false FMR curves and FNMR curves for the three different data sets. And this is for the original data, and this is for the data after we have gone and balanced the male and female subsets so that we would end up with a, as close as we can get, identical distribution of percent of the image on the face, right? When we do that, all of a sudden, women have a slightly better curve here. Where they had a worse curve here, you can't tell the difference. And where there was a worse one, substantially worse one there, it's really close and even a little bit better at the end. So we have managed to substantially improve the gap in accuracy between male and female accuracy, knowing no change at all in the training data, no change at all in the algorithm, balancing the test data so that men and women on average present the same amount of the 224 by 224 image as pixels on the face, which they do not when you just acquire the data.
So were you just doing that by selectively cropping them?
Yes, well, we cropped them, and then because there were more female images than male images, you can take a female image and find one that's kind of paired and close, and you end up with less data than you started with, right? Because you have to pair them. Okay, So if balancing female and male pixels on the face in the test images makes the false non-match curves nearly equal, then do we actually have a raise the lower to higher fix to the face recognition problem just by asking people to please pull your hair back so that it doesn't cover your face? And by the way, don't use extreme amounts of cosmetics, right? That's it. There's no algorithm. There's no algorithm change. And we got probably the second best of the 5 possible solutions to the problem. Is it possible that the data sets we're using to measure accuracy bias are biased toward finding bias? In other words, we're measuring things with tools that predispose us to see differences in accuracy that disappear when we actually equalize across demographic groups the content of the images. Okay. I'll stop and take questions if there's still time.
Yes, I think we have a few minutes for a few questions. If anyone would like to ask a question either online or in person.
Yeah, I have a question quickly, and people can probably hear me. So it's really interesting what you said, pull the hair back. And so that's a process change. And we all know that process changes don't necessarily work, right? Because process change means humans. Humans in the loop cause problems.
I'm not.
However, how about changing or modifying the male image such that it now has similar hair blockage?
For each male image that's presented, synthetically add the last female's hair to it or something?
Yeah, just let's cover those areas with something that's hair-like.
Well, but
Because, I mean,
that would be a reducing the good group to the accuracy of the lower
no,
group.
not necessarily.
No?
That's a modification to the data set. We don't know what happens to the performance.
Yep.
We assume, we assume the performance difference, right?
Okay.
But now we're training a new network on a
okay.
modified data set.
Yeah.
And from a CNN perspective, I mean, hair is just low gradient, right?
Okay.
So you can actually not really use hair. You can use any kind of technique to block that.
So the suggestion was not really a pragmatic and realistic one, except in very controlled circumstances that you would simply tell everybody to pull their hair back and not wear makeup.
Yeah.
It would give you much more equal accuracy. We wouldn't be here complaining about this if all the women's images had been done that way originally. Those headlines wouldn't exist. The result wouldn't exist.
Well, no. Headlines would exist. And here's why. In practice, we could not control the hair pull down.
Okay.
And then our networks would ultimately fail horrifically. My opinion.
Okay.
Disagree.
So we'll get to continue this a little bit later on, but I will give one other party an opportunity to ask one additional question if necessary. If you have one that's urgent. I don't see any in the room, and I can't tell if there's one online. But in the meantime, I'll ask one. Because you talked about the accuracy for African-American men. So what I'd like to basically make sure we are able to clear up now in terms of what does this mean in the context of the, like the performance is better for the African-American male, and how does that bear out in practice? And is it true? I have my own perspective on this. But
Is it true? Well, so if we went back and looked at the curves,
right.
African-American males for the same decision threshold are still paying a small penalty in false match rate, but they're achieving much more in false non-match rate reduction, right? So with the anchoring of the same decision threshold, they're losing something on false match rate and gaining a lot on false non-match rate. That's essentially what the larger D prime means.
Yes. And All right, and I'll pick up on that in the panel at 1:40. Because I think there's a little bit more to the story. Nisha, you have a question? If we could take it quickly, because we're ready for our next speaker.
Yeah, so I was thinking, do you think do we all really understand the feature vectors that come out of the network? Like what it is learning, like what the actual mathematical representation of the features itself is. So I feel like till we kind of understand that, like how are we actually going to say, oh, how are we actually going to define the causes of bias, right? Because we don't know. Yeah.
Yeah, I would say that I don't, and I don't believe that anybody does understand the feature vectors coming out of the trained neural networks. I don't think they have a clearly interpretable meaning. We can infer from experiments, changing one thing in the data as best we can, what the overall effect, but I'm not clear that we can tease that out of the feature vector.
Okay, with that, I'm afraid we're gonna have to stop here. Let's thank our speaker, Dr. Boyer. I'll turn this over to Dr. Rixenick to welcome our next keynote speaker.
Yes, thank you, Dr. King. It is my great pleasure to share with you the next keynote speaker. Dr. Nicole Turner-Lee is a senior fellow at the director of the Center for Technology Innovation at the Brookings Institute. She leads Brookings' artificial intelligence work focused on eradicating systemic biases in machine learning systems. Dr. Turner-Lee has a forthcoming book titled Digitally Invisible: How the Internet is Creating the New Underclass. And I'm hoping she'll give us an update on when that book will be released, or if it has been released. I would like to now turn it over to Dr. Nicole Turner-Lee.
Thank you so much, Carl, and hello, everybody, or aloha, if you're in Hawaii. I'm not, I'm in Virginia, sitting in the snow, but I'm actually happy to be here, and I'm glad I was able to catch a little bit of the presentation before me. So as Carl said, I'm excited to be here because at Brookings, I actually lead the Center for Technology Innovation, which is focused on regulatory and legislative policies affecting everything from the digital divide to spectrum policy to broadband deployment, privacy, among other things. And I also lead Brookings' institutional work when it comes to algorithmic bias. So we actually have 3 pillars, one related to national and international governance, bias, as well as national security. So I've actually been running that for the last 2 years. And I'm excited to be here because, as Carl said, I'm finishing a book, which is on the US digital divide, which hopefully at some point we'll be able to reconvene around that. It actually comes on the heels of qualitative visits that I did around the country prior to the pandemic, suggesting that the digital divide is no longer binary, but really much more multifaceted and much more complicated than ever before. And the pandemic virtually, basically exacerbated that. But more to come on that. But today's talk, I want to actually speak a little bit about facial recognition technologies, and particularly autonomous systems that I think that we have to actually have some cause for concern when it comes to greater discrimination and profiling. And so the work that I do at Brookings in this space is really looking at the intersection of race, technology, and social justice, and more specifically, what needs to happen to ensure the right technical cadence and the sociological implications of such technologies. I'm a PhD in sociology. I do not come with a computer science degree. In fact, I took a computer science class when I was in college. I was not able to move the cow more than 1 inch, and that was the end of my computer science career. So now I just stand actually at the center of these sociological implications because I believe if left unchecked, we're going to see a fair amount of bias that actually shows up in even greater precision than what we know systemic discrimination actually shows itself in external and the physical world. So with that, what I'd like to do is just sort of talk a little bit about how these generally purpose technologies are leveraging facial recognition and what we feel to be the problems from the policy perspective and how we need to potentially reel that in so that we create systems that are much more inclusive, much fairer, and honestly follow the laws of civil rights when it comes to their uses. When I think about autonomous systems, I like to share as the start of my conversation, that it is no secret that they basically have inundated everyday society. Whether it's a recent article that I read around driverless trucks that are actually helping us to support supply chain shortages, whether it's the use of the technology of AI in the identification and mitigation of the risks associated with the COVID vaccine, it's no secret that these technologies are more than what we used to say, that they're defining how we live, learn, and earn in society. And all of us on this conference would actually agree that this innovation is much more than we've ever imagined. When I was a little girl, I used to sit down and watch 3 cartoons on a Saturday afternoon. I would run home and watch something called The Jetsons, which was all about this 21st century that as a little girl, I had no idea that there would be autonomous vehicles and George Jetson would fly around in these space shuttles. You know, look what happened a few months ago. We actually took a commercial airline jet to space. And I used to watch Fred Flintstone, which actually drove around on trucks and cars that had rocks as wheels. And then the last cartoon that I watched, like every Black kid in America, which was Fat Albert, which was because their experience was very much like mine growing up. But with that being the case, we know that Fred Flintstone is no longer really around, that his existence has been obliterated by the use of technology. And we know that what George Jetson, for those of us who remember that cartoon, has actually imagined has come true. With that being the case, innovation always has the potential, I think, to create those greater efficiencies that really blow the mind of scientists and sociologists alike when it comes to the type of creative genius that we're able to harness. And I always look at it this way when I'm my studies around technology, that there are opportunities and perils that come with any creation or deployment of technological advancement. In the case of opportunities, as I've mentioned, we're seeing technologies help us through a public health crisis, a crisis around climate change, a crisis around, some of the areas where we've not been able to, with our own human intelligence, solve. But the perils come, and I think it was mentioned by the previous speaker in some of the questions, when those technologies are weaponized to support or amplify the persistent systemic inequalities that happen in the United States and across the world. Let me tell you what I mean by that. When we think about facial recognition technologies that are used in employment, we have screeners now called Emotion AI, where people are able to upload their faces so that employers can actually see the way in which they gesture, the raising of their eyelids, how wide their face actually shows sort of this inclusiveness or welcomeness for customers. But guess what we're finding about that technology? That technology, when applied to Black and Hispanic men, actually omits them from the candidate pool in employment opportunities, because unlike what we fought for and what new advances were made in employment to ensure that there were blind interviews or ways in which we would obscure the unconscious bias of employers, that technology, which presents facial recognition as part of its products, is actually discriminating and profiling those particular applicants. We also know that in the US criminal justice system, that we have caseloads among judges that can often confuse the ability to detain or release certain defendants when it comes to bail or sentencing. Well, guess what? We have a technological solution that allows us to make those kind of predictive analytics, but on the flip side of it, because we're actually dealing with data that overrepresents and oversamples Black and Hispanic men and women in the criminal justice system, that they're more likely to be detained than released when compared to whites. I'm going to go into it a little bit more in detail in terms of facial recognition technologies, but I share those examples, my friends, to let us know that in the end, these technologies, which were slated for innovative purposes, have perilous activities. They can be pernicious in their outcomes if we do not deploy what many of us in this room call fair, responsible, and I add inclusive and lawful technologies. When I think about facial recognition technology, and I found it interesting, the last speaker, just to think about the technical cadence that Carl knows has been advanced over the last few years, I do think that that's actually a good movement towards progressing towards more equal facial recognition deployments. But at the same time, if you go back to how I've actually set up this case, we have to be sure that we're not leveraging and inserting these technologies in contexts where we already see a range of systemic inequalities. Let me tell you what I mean by that when we actually look at facial recognition technology. Right in the middle of the pandemic, a Black man in Detroit was detained after the viewing by law enforcement of a grainy video for the potential of being one of the assailants in this particular burglary of a store. Let me go back to that. A Black man was actually picked up by the police after the viewing of surveillance footage at a grocery store, a local grocery store, I believe it was, and he was accused of being one of the assailants of this crime. That man stood in the law enforcement department in the police station for 6 hours until it was revealed that that was not him. So let me go back for those of you that are watching online or in person, just to re-emphasize that point. Robert Williams, a real person in Detroit, was actually detained based on the viewing of a grainy video wearing a hat. And I think this is something that the previous speaker actually spoke about, but he was detained by police under the premise that he was one of the people, one of the criminals that was set in that video surveillance of that store, but that was not him. Few years prior, Amazon released recognition software that many of you are familiar with that misidentified members, distinguished members of the Congressional Black Caucus here in Washington, D.C., who were misidentified when the software actually ran their faces through as criminal defendants who had mugshots that were already existing in the system. Third case, as it was mentioned, there are instances that my friend Joy Malami has actually pointed out where people like myself, Black women, who may be under poor lighting or may actually have changed their hairstyle or may be of darker skin that are not recognizable by these technologies, which again leads to either not being able to open my phone, or two, the potential misidentification of myself, me as a person, by law enforcement or some other entity because of the misidentification and the mismatch that exists in existing facial recognition database. I can continue to go down the line, but the most important reason why I bring up these examples, whether you heard them in this conference or not, is that on the perilous side of the application of these technologies, that it is important that we understand the context in which they are deployed and the extent to which there's not just differential treatment in the machine learning algorithms that may be designed empowering the model, but the disparate impact that it has on certain populations that are already over-criminalized, experience profiling and surveillance in their communities, and has long-term effects on those individuals who are now part of a system that either they've tried to avoid or one in which has absorbed their reality simply because of the historical underpinnings of our society. Now, don't get me started on this, and Carl knows me, that I'm one of those people that will dig in deep when it comes to the civil rights implications of these technologies. And I'm not necessarily suggesting that we ban these technologies entirely like many of my colleagues. I do believe that as we have seen AI become much more generally purposed in our society, that it is incumbent upon scientists and others like sociologists and lawyers and other types of academic disciplines to figure out ways to optimize those products to work accurately on other populations. As my friend Faye Cobb Payton, who is at North Carolina, actually says, if these technologies do not represent the lived experiences of the various subjects that they are working on, then we have actually created technology as its own tool to amplify systemic discrimination. And that is really the basis for a lot of the work that I do at the Brookings Institution. As a policymaker, I'm really tuned in on how do you create an ecosystem where in certain use cases that have already been proven to have detrimental impact and disparate impact on certain populations, particularly communities of color, how do we not embolden technology to play another role in facilitating that type of oppression? And I know I'm not alone because there are many scholars who have actually taken this on in a variety of use cases, from criminal justice to financial services to employment. But I share this, my friends, because I think for the scientific community, it's time for us to think about different approaches to how we look at technologies like facial recognition, to other uses of autonomous systems, so that we ensure that there is equity involved in their design and execution, and they're auditable. Because at the end of the day, none of these technologies will actually be for good if we can't go back and trace the audit the qualities and characteristics for how we got to those determinations. So I want to use the remainder of my time, and I'm open for questions. I cannot wait for questions and discussion, honestly, to talk a little bit about the backdrop of some recommendations that I think are useful to hear for this community. First and foremost, I think when we are talking about facial recognition systems, it is important to have increased diversity at the table when developing these models to recognize such limitations. Why it is that we're now discovering some of the setbacks when it comes to the facial analysis and detection is beyond me. We need to ensure that people in which we are deploying these technologies actually sit at the table at the point of development to ensure that what I call these algorithmic blind spots do not get baked into those models. And we need to ensure that type of diversity that I'm speaking about, because everyone on this call and in that room comes with their values, assumptions, judgments, and norms around the subjects in which they are contextualizing these models. So oftentimes, when I talk about facial recognition with folks, I often ask my scientist friends, well, why didn't you think about the implications of darker skin hues on these technologies? And what they commonly say is that they did not include them in their samples. Some of you may remember just a couple of years ago, Google was in the news because they were essentially taking pictures of Black people in the park to actually increase their sample of Black faces. That's not how we should be doing stuff. And we as academics know that when we are actually handling human subjects, that it's important for us to have a weight of variance or a weight of oversampling, particularly when we are making the judgment that this technology will be accurate on a variety of diverse segments. Friends, if we cannot figure out how to get more people to the table when it comes to diversity and cultural and racial and gender representations, then we are failing a whole discipline, where the technology itself is going to do what I think the opportunistic side of it, which is to help us solve some of the world's leading challenges. In the same breath, the reason why I love speaking before groups like this of scientists is that we need to include more disciplines at the table. In a paper that I wrote at Brookings, which is sort of the signature of how I got into this space a few years ago, is I wrote this paper on algorithmic bias identification and detection mitigation with a lawyer and a computer scientist. That paper was perhaps the longest paper I have ever written. A sociologist, a scientist, and a lawyer took us over a year. And it probably was the hardest paper that I wrote because the engineer kept telling me I was wrong, and I kept telling the engineer he was wrong. And the lawyer just tried to negotiate between the two of us. But it was the best paper that I wrote this space. And you know why? Because it allowed me to see different perspectives applied to one problem. In the area of facial recognition, it's very important that we have representative people around the table. We pull up additional chairs, but we also have people who understand the sociological, the economic, the political, the privacy, the legal implications of deploying technologies that not only have reputational risk to the developer, but have, again, the potential for unintended consequences where it actually defeats or devoids the purpose in which it was actually designed and deployed. And let me take it a step further in terms of those technologies. It's equally important, and this is something that I've been doing in my own research, that we think about the handling of those technologies so that we have the type of privacy guardrails in place, and we have the type of sensitivities when it comes to human subjects, the same way that we apply it in the social sciences, so that we ensure that we're not enduring undue harm among those subjects when we're studying them. So one thing, as I was listening to the previous panelists, I love the methodology in terms of changing up scenarios to have more accuracy in the identification of faces. But I also love the follow-up question in terms of the detrimental impact on Black males. We need to have systems in place when we're looking at these biometric and facial indicators to ensure that these subjects are not hurt in the end. The other thing that I would say is on data quality. And I'd like to bring up a point that my friend, Renee Cummings, who is at UVA, brought up in terms of data. We often talk about data quality in facial recognition systems because in many respects, the data is taken from overrepresented samples of mugshot data in many cases. We already know as sociologists that a disproportionate number of arrests happen in Black and brown communities over white communities for similar crimes. If that is the case, we are already starting out with a flawed data quality when it comes to whether or not that identification is going to be accurate or lend itself to mistakes. With that being the case, my friend Renee Cummings brought up a really great term that I told her I was actually going to use in every talk that I give this year, which is traumatized data. That there are data sets that we need to interrogate very carefully because they have been traumatized by the historical and social underpinnings of the societies in which we live. For facial recognition technologies that rely upon mugshot data, for example, that trauma of a criminal justice system that exhibits unfairness and is unequal when it comes to mass incarceration or overcriminalization, as a Georgetown study actually suggested that overrepresentation of those faces lends itself to very little variability with regards to matching. So it may have perfected match quality, but it actually is matching, as we saw in the examples I shared earlier, in ways that it's connecting associations much more frivolously than what it should. We should, friends, really be looking at this whole concept of the traumatized data in which we are relying upon. Now, it's very hard, don't get me wrong, to actually think about data sets that may be pure in terms of its use. And I know among scientists that they commonly tell me that they can mix and match attributes and characteristics to blind the algorithm somewhat so that it doesn't pick up on this noise. But I think, and this is something that Dr. Cummings picked up on and that I'm following along, is that this whole idea of unpacking traumatic data is important because it carries with it the sociological underpinnings of what that data emanated from. Some of you may disagree with me when we get to conversation, but that's okay, because I think part of the reason why we have these conversations on algorithmic bias is not necessarily because the science and math itself is flawed. It's because the context and the data that we're using to develop these models starts out of the gate with some type of infallibility. Let me share an example of that. When I think about criminal justice algorithms that actually are optimized to use by judges to help them in efficiencies, I think about the fact that we may be reducing error by 1 or 2%, but we're only reducing that error in a criminal justice system that already has huge spread when it comes to over-incarceration of Black and brown people. Meaning, we may be reducing it by a bit, but we're not necessarily helping to solve the problem that has already been laid out fundamentally. In my research, it's been really interesting as a policymaker to think about how you actually solve that. And one of the recommendations that I've made publicly is that I think that there are opportunities for government entities like the National Science Foundation or Congress to allocate money to NIST or to universities to build better data sets, ones in which are much more scientifically objective, but allow us to either oversample populations in different contexts. That kind of goes back to the conversation I picked up on when I joined the call. The third thing that I would say when it comes to facial recognition technologies and this bias that's embedded in autonomous systems is that we need to prioritize and distinguish between use cases. Right now, we are seeing in Congress a plethora of bills that are trying to solve this big problem, which has created its own legacy when it comes to just the public outcry of the use of these technologies and some of the mistakes primarily made by the private sector in the build it and break it first models that they actually deploy. But what I would say about this barrage of bills, we are also seeing, and I know this may be the conversation that we'll have later in the day, a confusion between the facial recognition bills and the biometric bills. We have right now a bill that was reintroduced in 2020 that was introduced first in 2020 and reintroduced this past year that is on facial recognition systems moratorium as well as biometric data moratorium. While in theory it makes sense, it is still one that is only allowing jurisdiction to federal entities and agencies. And that's why I think that this conversation of use cases becomes very interesting in facial recognition. NIST, for example, just published a piece that said that we're seeing a 99% accuracy rate of airport screeners that use face detection for identification. Because as long as there's at least one photo in the database, that it's more likely to positively recognize a person. But when you apply that to law enforcement, where you may have multiple faces or multiple conditions of that particular image, or it may not be a driver's license, it may be something else, it becomes much more hairy in terms of what the outcome of determination may be. Friends, why that's important is because in Congress, they're lumping it all together, but more importantly, they're trying to solve a problem that may be more wholesale than particularly designed for use cases. Or on the other hand, what we're seeing in municipalities is that we're seeing a lot of moratoriums and bans in local cities that are targeting law enforcement use and some biometric use. I know I've said a lot, so let me unpack this a little bit for you. Until we identify the specific use cases that we are trying to legislate and regulate, we will see facial recognition and biometric data sort of grouped into the same bucket with no clear understanding of what problem we're trying to solve. In a variety of cities, for example, we're seeing at least 16 jurisdictions at the local level that have passed bans or moratoriums on facial recognition and biometric use. But that's among law enforcement and federal agencies, not among private sector actors. And we're seeing something similar at the federal level because federal government pretty much has more jurisdiction over federal police officers or federal agencies where the limitations and restrictions are really levied against federal or public sector actors. Now, if you've been following me, you probably have picked up that the federal government and local and national and state governments are only one part of the problem. The bigger problem is the constitution of authority that is given to the private sector based on the fact that these publicly available data sets allow them to create products that are not necessarily designed in ways that take the care of weighted samples or the care of human subjects that look ahead at potential unintended consequences and mistakes. In my research at Brookings, and I have a book chapter coming out in the next few months in an Oxford University Press book on an AI, it's an AI handbook. I actually talk about a model that I'm developing called an Energy Star rating. And that Energy Star rating allows us to progress one step past NIST and allows both a technical cadence of best practices in particular use cases like employment, financial services, criminal justice. It allows for the right type of disclosures at the legislative level, as opposed to legislating the technology, legislating the processes that lead to the technology. Whether or not we disclose that facial recognition has these limitations when it comes to Black faces or lighting, whether or not we put in place civil rights laws that deter the type of activity that land up as unlawful consequences. And it also involves, as part of my Energy Star rating, a consumer feedback loop, where consumers are able to chime into the conversation and verify or validate whether or not those findings are them. Friends, to me, we need a much more collaborative and interpretable model, which is what I'm actually writing about in this chapter, to get to a point where we can look at these technologies for what they are and advance and innovate them in ways that they are much more inclusive and much more fair and responsible. If we do not do that, we're going to see, and this is where Carl and I actually had a great interaction when we first met each other, is that the more that we develop these technologies, without thinking through the testing and the documentation of these technologies and how they appear differently in a variety of contexts. I don't know if Carl remembers that conversation that he had on our Brookings stage. And the more we rush to ban these technologies versus understanding how to optimize them across segments of populations and segments of context, we're going to find ourselves recreating technologies that have reputational risks and consumer problems. And that's why I stand before you today as a sociologist, truly interested in this space. I will never go back to school and become a scientist. It's too late. But I will find myself within your communities, finding ways to advance and to encourage the type of collaborative work environment and interdisciplinary work environment, I think that lends itself to better consumer outcomes. And on the policy side, it's unfortunate that we don't have many of you that sit with us to better understand these models, because policymakers take things like facial recognition and confuse them with facial analysis and face detection without understanding the full maturity of these systems before they make the type of policy assessments and judgments. At the end of the day, it's just up to us to figure out what is the best framework for identifying and mitigating risk. And how do you, most of you on this call and at this conference who deal in the technical cadence side, figure out ways to look at specific use cases and organically build in gap stops that help us to reduce those blind spots. Having more people at the table who have the lived experiences of the subjects in which we're touching, ensuring that we deal with the trauma of the data that we're using, and ensuring that the use cases that we actually focus on have the ones where there's either most gain or most loss by consumers, I think is the first step forward. So I'm gonna stop there. Hopefully we can get into a conversation. Again, I'm so jealous, Carla, I'm not in Hawaii. I'm sitting there with you, but perhaps the next time. But thank you for having me at the conference. And I'm sure we'll have a great conversation, fingers crossed, on some of these assumptions that I want you to challenge me on if you feel that there's more discussion and dialogue we need to have. Thank you.
All right. Well, thank you so much, Nicole. This was an exciting sort of addition to this conference and to this particular workshop. I like your perspectives. I think you've challenged us in many different ways. As a technologist, I don't always look at the policy side of things, and we've had many discussions about that. I just said, leave me alone and let me do my work.
Right.
But I have to be more considerate of that. And we all have to be more considerate of that as engineers and scientists as we go forward to understand the ramifications of what we're doing. That should not stop the evolution of technology. That should not stop us from asking the questions and seeking the answers from a technical perspective, but it should inform us as we start to go down these roads that, you know, we have a bigger obligation, right?
Yes. Yes.
So I will raise my hand and tell many, my obligation was to the science and the technology, not to the use case for many years. Individuals like yourself and others that even come before you have, you know, helped to educate me on what my real responsibilities are as a technologist, as well as, you know, some of you guys know that I have a company, and these things have been pushed over to our company culture as we develop these algorithms as well. So with that said, I'm going to stop and ask for some questions because we will have a panel session coming up where we can go a lot deeper, but I think we have time for a question or two right now before we go to break. Do we have anyone with questions at this moment? Yes, we do. And then we'll go to the chat group.
Perfect. And I put in chat, so hopefully the people that are there, the paper I was referencing, it's at brookings.edu website under Turner Lee, my expert page, but it's the one on the algorithmic bias detection and mitigation best practices.
Hi, Dr. Turner Lee. That was a great talk. Thank you so much.
Oh, thank you.
Just wondering if there are any specific policies that you and the Brookings Institute are working now on pushing forward in this vein.
Yeah, so I love the question. Obviously, the Energy Star rating is one that I would love to get in place. I'm not proposing it as an enforcement mechanism. Some of you, just to get you up to speed, and my chapter will come out soon, I actually am looking at the Energy Star rating, which is a collaboration between the Department of Energy, the FTC, the Federal Trade Commission, and a couple of other governmental agencies that actually do the quality standards when it comes to appliances, their energy output, their water output, et cetera. I would hope to see some type of similar labeling system. We see this in Germany and other places in the EU, where we're basically putting out, and a lot of people call it the FDA label. I think that that's kind of a weird way to look at it, because how do you FDA label an algorithm? But you actually allow consumers some type of trust in the product, because they know that the algorithm, particularly in those use cases, has been sampled among a variety of populations, et cetera. So I'm definitely pushing that as a policy program that I think could be implemented to raise the level of trust within products that come into the online space. Because honestly, the reputational risk of a company landing on the front page of a newspaper because their algorithm detained a Black man for 6 hours is just not good. So we need to have some way where we know that there's a community, some better housekeeping seal around that. The other area that I think is really important now, and I've talked to a lot of legislators about this as well, is this whole idea of disclosure. So decision by disclosure. Many people in the country and many people online across the world do not understand that algorithms are often making those types of determinations. When it comes to facial recognition technologies, for example, many people don't know that those technologies are actually deployed within the stores that they shop at, or even in the airports. We know, and this is something I would love to share with this group, right? As a sociologist, we're familiar with the surveillance economy. Right? We know exactly the surveillance economy, and particularly the unequal conditions and circumstances in which they actually play out. But we as citizens don't understand, because it's not very transparent. We don't have these systems in place for disclosure and consent. Some of the biometric legislation that's coming out right now is trying to get companies, retail companies, to let people know that these systems are in place, or recording their biometric information, or using that as scans. We've got to work better on that. So from a policy perspective, disclosure, transparency, and that is really important. I think the last thing I would say that we're advocating at Brookings, and I think in Washington, DC, is some type of federal privacy standard. I just started playing with this argument that possibly algorithmic bias is a consequence of the lack of privacy legislation, because we can pick up on all these attributes pretty much without any type of constraint. And those lend itself to many of these mistakes that we see playing out in the real world. So perhaps we need better privacy legislation. And we're seeing that with the Facial Recognition and Biometric Act. We're seeing that across the board in terms of municipalities, as I've mentioned, that we're really clear about the large scope use of these technologies before we start legislating particular use cases. We're doing a project at Brookings right now on facial recognition technologies. I'm doing it with my friend, my colleague and friend, Rashawn Ray, who's more of a criminologist in sociology. And what we found is better training could be helpful, or potentially the use of facial recognition technology in alignment with other technologies like augmented reality and virtual reality. He has a lab, the University of Maryland, where they're actually helping police officers through AR and VR understand stressful situations. And we've been talking about, if you infuse FRT in that in a constructive training context, can you actually improve upon its outcomes as well? Because listen, don't get me wrong, we needed facial recognition for the January 6th insurrection. We needed facial recognition for the Boston bomber. But what we don't need is the excessive use of it in law enforcement agencies that are not properly trained to understand the implications of how it's actually panning out.
Hi.
Hey, I listened to your presentation, right? Were you?
Okay, and we can interact over that later.
Yeah.
We in the technical side, we're used phrases that are popular right now are interpretable AI, explainable AI, trustworthy AI, and probably some other synonyms for those things. You use the term auditable, which I think is similar but different, and wants more of some other things that are not in the terms that we're more used to. So could you tell us what audible is, auditable?
I know, right?
And how it's different than the things we're already used to talking about or used to thinking about.
Yeah, no, I love it. So the reason why I use the term audible now is because I think policymakers are not engineers or computer scientists. So when they say things like, I need this AI explainable, I need you to tell me how you arrived at this model. For those of us in this room, what we know is that these are organic models, that once they're deployed outside of the classroom or outside of the lab, and they get deployed in real world context, they actually pick up other inferential data that may change the nature of the model when it comes out of the end of the black box. And so I really have moved away, particularly with legislators, of having them jump to the gun of saying to companies, for example, give us your code so we can determine whether or not there was explainable in terms of its outcome. That's not going to happen. First and foremost, these systems are so opaque that it's hard for us to determine the point of impact if there was a disparate impact or differential treatment that occurred. And the second thing that we know about these systems, that policymakers are primarily interested in the outcomes and not necessarily interested in the development as much as they think. And so if you can create, I think, models that are auditable, we're actually starting to see a lot of that tracing in researchers. Data and Society, I think, has a lot of people looking at that. Auditable in terms of the impact of that particular model on certain outcomes. Audible, we saw this with Facebook recently where they put out a report on civil rights implications of their models. Auditable, where we can actually trace what I'm still working through this model, but sort of the occurrences that happen that may indicate a blind spot, or it may indicate where there was a disruptible model. The reason why I share that too is in my research as part of the Energy Star rating, I've been looking at various sectors to see how they look at their algorithms. In the financial sector, for example, they're highly regulated. So they have litmus tests that have to be auditable so that they can go back to the banking regulators and say, the use of this zip code was not used as a proxy for eligibility on a mortgage. We have products right now, and particularly in spaces like facial recognition, where they're more consumed into larger products. So they're not necessarily the product, they're just sort of the engineering of some of the products. It becomes harder for us to figure out whether or not we're looking at the AI of facial recognition by itself, or whether or not we're looking at it within the context of something else. And so again, I'm trying to move policymakers and scientists to a stage where we can determine better cadence on the technical side, where you can go back and say, okay, where was that failure? Despite the fact that I inserted all this noise, it still landed up giving me a collective response, as LaTanya Sweeney's work suggests, that surveilled or profiled certain populations, versus where can I actually see the interpretability of this model, which I think is like, what does that mean? To people who are trying to understand why my technology excluded Black patients from a healthcare algorithm. So I hope that explains it. I would love to have more conversation. I'll put my email and my Twitter on here for other people who want to talk more about that. But for me, and Carl knows this about my work at Brookings, it's about making this stuff palatable for policymakers who are not technical engineers. And where do you keep them in their lane, while at the same time, as Carl mentioned, giving the technologists some sphere of responsibility to work from. And that might be it, creating these gap stops where you can go into the technology and say, how did it perform at point X? How did it perform with this type of face? How did it perform with this type of context?
All right, this is wonderful. I'm sure that we have many more questions, but I would ask us to hold for the panel session, because we have some really important things like food that's coming up. So we will have a break, and we will return exactly at 1 p.m. HST, 1 p.m. Hawaii Standard Time. And we will have 2 exciting papers and then the panel session. So I encourage you to come back. These are going to be some really cool papers. Don't miss them, and certainly don't miss the panel session. It's going to be fire. Thank you all. I'm going to pause the recording now, and we will see each other at 1 p.m. HST time. Thank you.
Thank you too. I'll see you later.
Hello and welcome back. We are going to take on the second half of this workshop. We have 2 exciting talks that are coming, and then we have a panel session. Recording has started. And I will start in just a moment with the following talk that was pre-recorded. Got to put my glasses on at some point. This is similarities in African ethnic faces from the biometric recognition viewpoint. We have with us a representative of the authors, who is Pat Flynn. I will start the start the presentation in just one moment. Okay. And voila. And here we go.
Hello, everybody. My name is Patrick Flynn, and I'm a professor at the University of Notre Dame. Ogechukwu Iloanusi from the University of Nigeria, Patrick Tinsley, a graduate student at Notre Dame, and I are the co-authors of a paper entitled Similarities in African Ethnic Faces from the Biometric Recognition Viewpoint. Here's an outline for today's talk. We'll begin by stating research objectives. Following that, we'll introduce some concepts from facial morphometry and heritability, focusing both on global studies and studies within Nigeria and its distinctive context of ethnic diversity. We'll discuss a data collection that was performed in 2018 and 2019, in which many images were captured from Nigerian subjects across a number of different sub-ethnicities. We'll also discuss a data set that was assembled here at Notre Dame from many data sets collected during a 10-year period. We'll talk about some experiments that were conducted that were intended to address different aspects of the problem of facial recognition from multiple ethnicities. We'll provide some assessment of the results and some possible directions for future work. The objectives of this work are to analyze the performance of face recognition algorithms on gallery and probe sets composed of different faces of African and/or Caucasian Asian ethnicities. We want to use an acquired database of African faces collected in Nigeria and Caucasian Asian faces collected in the United States over a 10-year period. We define 4 major experiments that are conducted on these data sets. In addition, we report on face detection yield for these 2 data sets. Nigeria is a large and very diverse country. It is the largest nation in Africa by population. It is the 7th largest nation by population in the world. The map at right depicts the ethnic diversity of Nigeria. There are over 250 sub-ethnicities across the 36 states in Nigeria. The tendency of genetic factors in Nigeria to be conserved is driven by the pattern of endogamous marriages. This tends to reinforce genetic characteristics, and one of the ways in which this manifests is in the conservation of facial characteristics, which can differ from sub-ethnicity to sub-ethnicity in the country. Nigerian residents will routinely say that they can tell the sub-ethnicities apart from one another based on facial characteristics, but these factors can be hard to describe. The distinction between faces among the sub-ethnicities in Nigeria has been studied, and there has been some prior work in the development of automated systems to distinguish between sub-ethnicities. Facial morphology and heritability, and in particular, the association of genetic factors to the conservation of facial morphology, has been studied in several prior works that address Korean families, British subjects, children in Africa, adults in Africa, the Han Chinese, and multiple European groups. There have been several studies specific to Nigerian citizens of facial anthropometry. These studies generally employ the nasal index and the facial index, which are ratios of 2 geometric quantities each. These Nigeria-specific studies have examined the distributions of these indices across several ethnic groups. The novel Nigerian faces dataset was collected between June 2018 and December 2019 at the University of Nigeria. 551 subjects were captured in total, of whom 356 were male and 195 were female. 134 subjects appeared in more than one session among the 3 listed on this table. The stills used in the experiments reported here were extracted from face videos that were captured with a standoff of 500 millimeters to 1200 millimeters. During that video collection, subjects were requested to display 8 different facial expressions based on emotional labels and to reposition their head among 5 different poses. This slide depicts the 8 different facial expressions that, again, were prompted from the subjects by the collection operator. This table depicts the 28 ethnicities represented in the African Faces data set. And the first thing you will notice is that there are almost 500 subjects from the Igbo ethnicity and only single-digit numbers of subjects from all the other ethnicities collected. As a practical matter, obtaining a truly balanced data set from these 28 ethnicities or more ethnicities within Nigeria would require extensive travel, extensive expense, and security concerns. The imbalance is accounted for, in a sense, in our later experiments, but we acknowledge this as a weakness of the work. We now provide a brief description of the Notre Dame Faces data set, which was assembled from a large set of facial images collected over a 10-year period at the University of Notre Dame. The images in this data set were acquired across 7 different recording sessions. 610 subjects were included in this database, 313 males and 297 females. And there is a total of 7,728 high-resolution frontal face images. There are 479 subjects who identified as white and 131 who identified themselves as Asian. We conducted 4 recognition experiments and 1 detection experiment in this work. The first 2 recognition experiments address recognition within the Nigerian database among the different ethnicities. Experiment 1 dealt with recognition performance among a multi-ethnic data set or within a single ethnicity. Experiment 2 replicated experiment 1, but with the addition of imposter subjects to the galleries involved. Experiments 3 and 4 were studies of the location and spread of genuine and imposter scores among Nigerian, Caucasian, Asian, and for imposter scores, Caucasian, Asian matched to Nigerian face images. Finally, the detection experiment examined the performance of DLIB versus HAR wavelet versus MTCNN versus retina face approaches to face detection across the 2 data sets involved. We now provide some details for experiments 1A and 1B. Experiment 1A employed a gallery containing subjects from 27 mixed tribes, a total of 62 subjects, 24 female, 38 male, and a total image count of 1,348. The probe set contained 18 subjects, 12 females and 6 males, and 536 images. In experiment 1B, the gallery set consisted of 62 subjects, 24 females, 38 males, and 1,470 images. And the probe set contained 18 total subjects, 12 female, 6 male, and 538 images. Experiments 2A and 2B correspond very closely to experiments 1A and 1B. The difference between 1A and 2A and 1B and 2B is that the gallery set is expanded to include 409 imposters for whom no probe image will correspond. 149 female subjects, 260 male subjects, 8,917 images composed this expanded imposter gallery set. So in experiment 2A, the gallery set from experiment 1A was added to the expanded imposter gallery set just described for a much larger gallery set than in experiment 1A. And similarly, for experiment 1B, the gallery set was enlarged by adding the same imposter set. We now move on to a discussion of the results of experiments 1A and 1B. You'll notice in the graphs on this slide that there is a red curve and a green curve. The red curve depicts the distribution of imposter scores. The green curve depicts the distribution of genuine scores. I should note that the arc face matcher and its L2 distance score computation are used in this work. In experiment 1A, which involved matching between mixed ethnicities, we see a D prime value of a very nice 3.832, an area under the curve close to 1, an equal error rate of 0.4%, and generally good separation between the 2 distributions. Similarly, for experiment 1B, that dealt with recognition within a single ethnicity, we see a D prime value of 3.84, indicating good separation between genuine and imposter score distributions, and an equal error rate of 0.17%. We now move on to a discussion of experiments 1A and 2A. Recall that these experiments differ only in the composition of the gallery. Specifically, experiment 2A uses a gallery set that contains a large number of imposter matches, matches with no correspondent in the probe set. When we examine the results, without this enhanced gallery set, again, the D prime value 3.83, the equal error rate 0.4%. When we consider experiment 2A with an enhanced gallery set, the D prime value hardly changes at all. The equal error rate decreases, but only slightly. Similarly, the results from experiments 1B and 2B, which again differ only in the composition of the gallery, with experiment 2B containing a larger gallery with many imposter matches, the D prime scores are very similar between 1B and 2B, indicating very little change in the position, spread, and relative errors associated with the match and non-match score distributions. Shifting gears slightly, experiments 3 and 4 were intended to depict the relative position and spread of genuine and imposter score distributions for within and between ethnic groups among the Nigerian faces and ND faces data sets. Specifically, the brighter green distribution on the left, the broader distribution, is a distribution of genuine match scores within the Nigerian faces data set. The darker green curve depicts the distribution of match scores within the Notre Dame faces data set. The three curves on the right all depict imposter score distributions. One, with an asterisk marker, is the imposter score distribution within the Nigerian faces data set. The second, with an X marker, depicts the imposter score distribution within the Notre Dame faces data set. And the third, with a plus marker, illustrates the imposter score distribution for matches that involve one subject from the Nigerian faces data set and one subject from the Notre Dame faces data set, therefore an imposter match. What we see generally is that the Nigerian faces imposter score distribution is broader than the other two, and that matches between the data sets are the least broad, with the Notre Dame faces in the middle. While the general characteristics of the distributions for match scores are similar, and the characteristics for the distributions of non-match scores are similar, we see differences in spread and some suggestion of a difference in location among the match scores and non-match score distributions. A number of possible causes suggest themselves. It could be due to image collection differences, to subject-specific characteristics, or to ethnic-specific characteristics. We do not have strong evidence that these are due solely to racial differences because of the experimental design. This area needs more study. The findings suggest that ARC face may have been implicitly tuned by training to the Caucasian Asian face domain and might require some retuning to obtain similar performance on African faces. The findings also suggest that same subject face images in the Nigerian faces data set are more spread out in latent space than same subject face image matches in Notre Dame faces. And finally, there may be merit to investigate broader tuning to develop systems that are robust to demographic variations. This slide depicts the results of a fifth experiment that we conducted to investigate face detection yield among the two data sets. We employed 4 different detectors: HAR cascades, the DLIB detector, MTCNN, and retina face. And with the exception of HAR cascades and possibly MTCNN, we see roughly equal performance between the two databases in terms of face detection yield. The HAR cascade method was the technique that showed the largest discrepancy, and one of the possible remedies would be, again, retraining with a more diverse data set. To wrap up this work, I'd like to point out a few contributions that we believe we've made. we've done a first study on the influence of Nigerian ethnicity on face biometric identification performance, somewhat limited by the fact that the data set we collected is quite unbalanced and low in numbers for non-Igbo ethnicities. This work also provides a comparative study of genuine and imposter match scores between African faces, Caucasian Asian faces, and between the two data sets. Finally, the Nigerian faces data set, like the Notre Dame faces data set, will be made available to researchers who wish to investigate some of the issues raised in this work, as well as explore their own hypotheses regarding face recognition performance and the influence that ethnicity has on that performance.
All right. So we now have time for some questions. We have Dr. Flynn available to address questions. We'll start in the room.
I'm in Hawaii. Is the variation in facial expression for multiple images of the same person much broader in the Nigerian data set than in the Notre Dame? And does that make any difference? Is that the cause of any of the things you saw in the results?
I believe in these experiments, we only use the neutral expressions. And so within those neutral expressions, I can't say with confidence that there is a difference in spread of within neutrality between a significant difference between the African faces collections and the Notre Dame collections. It's possible that there is a difference, but I do not know. This is something that I can confirm with the other author of the study.
Right, thank you. Do we have any other questions from the audience, the in-person audience? All right. Do we have any questions from our internet audience? All right.
Carl, I do have one.
Yes, sir.
Hi, Pat. Thanks for the presentation there. I had a question about the data collection process itself. So what kind of additional metadata was collected during the course of the acquisition of the data?
The Nigerian collections were performed by the first author of the work. And I believe at the time she did the collection, the metadata was not dissimilar to what we collected at Notre Dame. So we knew approximate year of birth, certainly gender as reported by the subject. There was no need to capture race because there was just one race involved, of course. Again, I'm not certain that anything else was collected, and I could try to dig into the database to see what the spreadsheet contains, but it's not a lot more metadata than Notre Dame had, and it's possibly less.
Okay. Okay. Can I ask a follow-up question? The distinctions between the various groups, were there any evident markers on the face? I can understand morphological markers, but were there any other cultural markers that were evident as well?
That's an excellent question. This did not come up in our conversations, and I can certainly follow up on that because it is an interesting question. In certain parts of the world, there are, of course, ritual facial marks, various ornamentation that's done on the face. I do not know if any of those apply in this data set, but if they are present, then it should certainly be noted in an expanded version of the work. That's a great suggestion. I appreciate it.
Thank you, Pat.
Thank you.
Thank you, Pat, for representing this paper and all the great work that you've done.
Thank you.
Have any further questions, please feel free to reach out to Pat and the authors. And Pat, maybe you can put your email out on the chat group, and maybe a link to how to access the data set would be helpful as well. These recordings should be available within the next 24 hours, according to Terry. All right, so we're going to move on to our next paper. And this paper is a analysis of manual and automated skin tone assessments. And I will get that loaded up for you in just one moment. Oh, well, let me go and share the screen just really quickly. Let's see.
I'm Gabrielle. Sorry. Let's restart. All right, that was my test run, everyone. Okay. Hi, I'm Gabriella Pangilinan, and I'm here to present an analysis of manual and automated skin tone assignments. This is a joint work in conjunction with Drs. K.S. Krishnapriya from Valdosta State University, Dr. Michael King from Florida Institute of Technology, and Dr. Kevin Boyer from University of Notre Dame. Our research is led by three primary questions. How consistent are manual skin tone ratings across different observers? What is the variation that exists in manual ratings of the same face image? And how do we even begin to compare manual and automated skin tone ratings? We're motivated by recent news reports and articles, as Dr. Boyer touched on this morning, of noting that dark skin tone is a cause of increased error in facial recognition algorithms. So in 2018, the New York Times reported that dark-skinned women faced up to 35% less accurate facial recognition as compared to white men. And in 2019, the BBC reported that since the original data sets were primarily composed of white men, gender and race are problems. So there are three skin type classification schemes that have been used historically. The first is the von Luschen scale, which was developed in the 1900s. And with this method, opaque glass tiles were pressed against the subject's skin in order to classify them into one of these 36 categories. This was a pretty inconsistent method across different observers, and so usage stopped in the 50s. The Fitzpatrick scale was developed in 1975 for dermatological research, and it's based on whether skin tone tans or burns when exposed to UV light. In the late 1990s, individual typology angle, or ITA, was developed, and this is a way to measure skin tone from computer-based images using the equation shown on the bottom here. So all three of these schemes have different strengths and weaknesses. And so we work to develop a way to scale ratings based on computer images using a Fitzpatrick-inspired method. In this study, we use the MORPH data set, which is a collection of mugshot-style images with controlled acquisition. The African-American male cohort of the MORPH data set has 36,000 images of 8,850 male subjects. And in our study specifically, we focus on 1,871 images from the center and high similarity tail, or false match region, of the African-American male imposter distribution. At a high level, the way that our procedure worked was that we began by color correcting images based on the known 18% gray background used in the acquisition of the MORPH data set. And we had manual raters assign skin tone ratings to the full face images. Then we used face skin masks, as shown in the image on the right, for automated ratings. Pre-processing was a really crucial step here in order to normalize both skin tone and background for images shown to manual and automated raters. So we begin with the original image all the way on the left there. First, we segment out the person from the background, and then we remove the gamma nonlinearity. So gamma nonlinearity is a factor that is applied to the pixels of an image shown on a computer to optimize viewing on a screen, but we need to remove it in order to determine what the true background color is, if you will. So we calculate the mean background pixel value of the linear image with the gamma nonlinearity removed, and then compute a color correction factor based on the 18% gray. Finally, we add back the gamma nonlinearity to get the final image on the right. So on the bottom here, we have an example of original images from the morph data set. As you can see, the backgrounds don't look gray and the skin tones look a little funky. After we did the color correction step, the backgrounds appear to be that nice gray. So for the manual skin tone assignment, we developed the apparent skin tone scale, since the Fitzpatrick scale, strictly speaking, is meant to be used in person and by a trained practitioner. Similarly, it's a 6-tone light to dark scale, and it is guided by exemplar images shown here from the well-known IJBC dataset. So our 6 human observers independently viewed all of our 1871 images and assigned an AST rating. Ultimately, we used the mean rating of all 6 ratings per image as the consensus manual rating. So our 6 manual raters agreed on an AST rating for 46 of the images with no difference in skin tone, 966 within a 1-tone difference, and 1,604 within a 2-tone difference. For the automated process, we used ITA measured from the color-corrected images. So we begin by face detection with DLib, and then face skin segmentation using BiCNet, and finally we threshold on the CBCR color channel. We then use the ITA equation as shown in the previous slide to determine what the ITA value is. In order then to relate the manual and automated ratings, we mapped the consensus manual ratings onto the ITA scale to determine optimal thresholds. And as we see here on the right, we have this ITA value mapped to the AST skin type of 3. One question that arose in the course of this study is, what is the influence of skin tone on false match rate? That is, are the images in the high similarity tail, the false match region of the imposter distribution, different significantly in ratings, in skin tone ratings, than images from the center? So ultimately, we presented 959 images from the center of the distribution, 933 from the high similarity tail, and 21 images were in common. So as we can see here with this graph, on the bottom, we have yellow and green are the manual ratings from the center and high similarity tail. Blue and red are automated ratings from the center and high similarity tail. There didn't seem to be a big difference based on location in the imposter distribution. And so from that, we don't really find any clear support in this study that images with darker skin tones occur more frequently in false match pairs. As you can see though, the manual ratings were much more clustered around the 4, 5, and 6 skin tone, whereas the automated ratings were much more spread out between 1 and 6. So the automated rating and the consensus manual rating agreed on the skin tone for 466 images with no difference, 1,379 within a 1 skin tone difference, and 1,771 images within a 2 skin tone difference. And again, from the graph here on the bottom, we can see that there really isn't that much of a difference in the skin tone rating, either automated or manual, based on the location, the image or image pair's location in the imposter distribution. So what were the reasons for these variations? Well, the manual raters were viewing the full face images as we see here on the left, while the automated rating was assigned to the face skin masks on the right. And so we postulate that one of the reasons for the variation was that humans are able to contextualize the image. For example, consider how a person's pose or the lighting might be affecting the estimation of skin tone. So they might ignore areas of overexposure or underexposure and look to the more well-exposed areas of the face. The automated rating system obviously doesn't have the same ability to contextualize, and so they are just going purely based off pixel values in the image. So a way that we want to mitigate this problem in the future is by just showing both manual and automated raters clips of skin from well-exposed areas so that they're only looking at that and there's no bias and no context. So ultimately, this is a really challenging problem, both for humans and automated raters. Human ratings are often inaccurate. So here in the top row, we have misclassifications from the manually annotated IJBC data set. From left to right, we have images that were annotated as being skin tone 1 through skin tone 6. But if we look at these, it's pretty clear that we get that these are pretty much exactly the opposite of what they should be. The automated rating systems that have been used historically are also, also struggle a lot, and they're very affected by lighting, poor resolution, et cetera. So on the bottom here, we have automated annotations from the DIF data set. These images all have ITA values that map to the skin type dark, but obviously looking at them, they appear pretty light. So it's a tough problem for both human and automated raters, but it is obviously important for us to develop good ways to estimate skin tone from computer images in ways that are scalable and as accurate as we can get them. And that's it. Thank you.
All right. So we have Gabby here in person. So we will jump to questions. All right. Any questions from anyone in the room? No questions from anyone in the room. Okay. And do we have any questions from any of our participants online? All right.
Carl, I have a quick question.
Yes, sir.
Gabriela, thanks for your presentation. The question I have is it important to ensure that we get the right skin tone in order to perform face recognition? I completely understand from the perspective of understanding differentials, but for performance of face recognition, what are your thoughts? Is that something that has to be very accurate in such a way that it can be positively incorporated into the recognition pipeline? Thank you.
Thanks, Dr. Ross. I'm not sure the extent to which it is necessary for the accuracy of facial recognition kind of in a vacuum, but obviously, as we've been talking about today, as we try to analyze these algorithms and figure out where they're going wrong on people of color and women and all the other demographics that facial recognition has historically performed poorly on, I think it's important for us to be able to develop automated methods in order to provide this metadata to the existing data sets. So that's an issue that we have had when we're looking at these things, is there aren't very many data sets that have these annotations, because it obviously is very time consuming to go through them and individually annotate. And again, the ways that annotations have been provided historically have been either in person or with these kind of newer computer-based methods. So we're kind of working towards developing better methods for the scalable annotation of data sets.
Thank you very much.
All right, thank you.
Just in case, let me check really quickly. Any more questions? Do we have any more questions? I don't think so. So thank you again. Let's a round of applause. So this leads us into our next session, which is the panel session. Oh. And I believe that we have a moderator for the panel session, which is going to be Dr. King.
Yes, I'm right here.
All right. We have Kush, we have Misha, and I'm not seeing Nicole Turner-Lee on at the moment, but we will continue on with this session. And I am certain that there are going to be some interesting questions and some dialogue between the panelists.
How do we want to do this? Because this is the first time I've actually had to, I've moderated a number of panels before, never with people somewhere else in the world and physically in the room. And so just do it. Huh? All right, cool deal. That's what I'll do. All right. So look, let me go ahead and start by saying the what I normally say whenever I'm talking on this particular subject. I'm a very friendly person, and I mean well for everybody. Some of these topics get to be kind of touchy, and so if I say anything to offend anyone, either in person or online, I charge it to the head, not to the heart. It's not one of those things that is intentional. But I will jump right in to, and here is Dr. Nicole Turner-Lee joining us now. So I'll jump right in by saying that one of the primary drivers for a lot of the work that we've been doing in this space, or that's really been driving the need for a workshop like this, and my own personal work with in collaboration with Notre Dame in this particular space, has to do with, the potential of kind of false arrests and those types of things. And so, to date, we know of 3, false arrests to occurs where face recognition technologies was used. Now, Dr. Boyer is my friend here, and so I I was kind of chiding him a little bit earlier on one of the statements that was made in terms of face recognition being the most accurate for or performing the best for African Americans, African American males, to be more specific. And so, in jumping right into the questions, we have face recognition accuracy being most accurate for African American males, yet 3 false arrests have occurred, 2 in Michigan, 1 in New Jersey, of African American men based on perceived false matches using the technology. All right, documented false matches using the technology. Yeah, you gotta come to the mic now. So help us to reconcile how it can be that this technology is both the most accurate for this particular demographic of the African American male, yet has produced 3. The use of the technology has yielded 3 false arrests. And I'll step aside here. I know we've had this discussion, so.
Well, but before you answer that question, I have a question. So your results that show the D prime for African American men were done on a particular algorithm.
Yes.
Was this the same algorithm that was used for these cases?
So as the moderator, let me try and control this a little bit. Let's hear from the speaker first.
Okay.
And then you can ask your question, sir. Sir.
I think Mike is enjoying the feeling that he's putting me on the spot here. Okay. The sense in which face recognition offers the most recognition power for African American males. Okay. I'm going to step away from the police thing for a minute, but I'm going to come back to that. Let's say we're doing photo verification to get on the airplane, right? My passport already records that I'm male and that I'm Caucasian. It can use a passport for male Caucasian threshold, matching threshold for male Caucasians that's going to give 1 in 10,000 false match or whatever you want. Your passport can do the same thing. You're going to have a different threshold than I am. One of the ladies from the audience her passport would have a different threshold, right? We all are going to get the 1 in 10,000. This is facial verification, right? You're going to get the lowest false non-match of the group.
Using the same threshold.
Yeah, okay. Well, it's a threshold, 1 threshold for all. Okay, so you're going to get the best performance. Now, with regard to the 3 instances, I think they are all officially, by the jurisdiction which originally performed the arrest, acknowledged and admitted to be false arrests, because they've apologized, they've given money back, in the different cases. So I don't think there's any question they were all false arrests. And I would ask, do you think that the incident would have been better prevented by changing the facial recognition algorithm or changing the police officer investigating? And there's a strong implication there where the problem is, right?
Are you asking the moderator or are you asking?
I'm saying that's a rhetorical question to everybody who thinks about this. Are you seriously telling me you're going to change the algorithm and get a different result? I have no confidence in that. You're going to change the person or change for another person who's interpreting the information that comes to them and acting on it. Yeah, I think you might get a different result. I think some people are acting incorrectly on the face recognition information they get, and they either need better training or to be replaced.
So
That would be my opinion.
I'm sorry, I have a question about that because you have three different scenarios. And so there are probably three different processes by which they use the technology and they go out and make the rest.
Hold for 1 second. So those of you who are online, can you hear what Dr. Rixenick is saying? Yes, okay, good. All right, continue, sir.
Yes, sir. And so do we understand those processes? Because 12 years ago, there was this organization called FISWIG that stood up best practices that simply stated to sum down these documents, which are currently online now, that said that there should never be used face recognition for automatic detection. There should always be a human in the loop and a process by which to validate through the human process the identity.
So there's one of the cases I can call to mind in particular. There's a photo on a driver's license that was matched to, that was the gallery. There was a photo from surveillance in a store that was the probe, right? The photos come back to the policeman. The policeman believes that investigation consists of going to a store, mall cop person at the store and showing who was not there when the incident happened and showing them the pictures and asking if this looks like the same person. So yeah, I understand that process, and that process is a failure. That's not investigation, right? I mean, that mall cop has no more experience or expertise to claim that those photos, he's not an eyewitness, has no special expertise. That should not have counted for investigation either to the policeman doing it or to the person who signed off on the arrest warrant. So we had two different person mistakes there, just inexplicable. It was not investigation. You shouldn't have thought it was, and your boss should not have signed off on it to be, in my opinion.
Okay, all right. So are there any other, we got a hand raised by Nisha,
I
yes.
expect Nicole to chime in here.
Yeah.
I had a question, but in an operational scenario, do we actually know that they're using different thresholds for different demographics? Do we know that? So right now, I think they're just using one single threshold, operational threshold, right?
Yes.
In an operational scenario.
Yes, no, we've had this discussion before. The feeling is that is my individual feeling is, and I'll let Dr. Boyer kind of, today, using in today's technology realm, it is intractable to be able to use a different threshold for different demographic groups. And from a law enforcement perspective, I think you'd run into, when you begin to look at the legalities of such, using a different threshold for different demographic groups, I think you'd run into some trouble there. Now, that said, I think in time, we will end up in a situation where the algorithms themselves will be imbued with the capability to extract different demographic attributes and maybe make some type of compensation based on the demographics, but it won't be one of those things that's easily explainable, at least in today's technology. That's my personal view. You feel,
Yeah,
yeah, you go
I
ahead,
think
man.
we don't officially know what thresholds people are using, it's very unlikely that there's widespread practice of different thresholds set in the system explicitly for different demographic groups. So once you've gone into deep neural networks, you don't really know.
Yeah.
You just don't know.
Yeah.
Right.
Can we ask Nisha from, if it doesn't get into corporate secrets, are they looking at dynamic thresholds?
Okay, that's an interesting question.
What did he say? I didn't hear what he said.
So the question is, from a corporate perspective, is your organization developing face recognition technologies with dynamic thresholding capabilities?
We're exploring along those lines because we want to have something that's generalized as well, right? Because our clientele come from across the world. We're not focused on clients within the United States. So we have clients across the world. So we want to make sure that our algorithm works well for all of them. So we are kind of exploring that.
Okay.
And maybe we're going to have a prediction system within the algorithm that will tell us maybe the ethnicity and then make a prediction on that.
Okay, that would be very interesting if once that is actually deployed. Dr. Turner-Lee, and then I'll go to Dr. Varshney.
So this is more of a question, though. I do have a question because I have heard the private sector talk about confidence factors and whether or not they, instead of talking about thresholds, they talked about the confidence thresholds where, and maybe I'm not sure if you're talking about the same thing, so I'd like some clarification, where there's been some refute of data by independent scholars because they feel the confidence metrics are too low or been reduced down, that creates the confusion or shows the inaccuracy. So I'm curious, just for my own explanation, are you all looking at thresholds at the same as confidence factors, or is that something different? Because again, I've heard Amazon, for example, suggest in Joy's work that the confidence factors were off in terms of what they tested the data at versus what an independent researcher has tested the data at. And that's sort of their way to back out of some of the noise that's actually created by misidentification.
So I'm going to ask Dr. Nisha to answer this first, but then I'm going to ask Dr. Varshney to kind of clarify the confidence thresholds, even though you said, but for face recognition in one of your slides, the work that Joy Bolawini was doing was aligned more closely in the area of facial analytics as opposed to face recognition.
Yeah, thanks for the clarification. But you know what I'm talking about. There's been like some pushback on confidence based on like some of the independent analysis. So I would be curious to hear what other researchers say about that. Thank you.
Let me ask Dr. Srinivas to respond from a face recognition perspective, and then I'll ask Dr. Varshney to respond from just a recognition or classification rate confidence interval with doing classification.
So I feel that when we use the term confidence, we're talking as a classification problem, or any classification or facial attribute prediction. We say, okay, with so much confidence, my network is saying that the person is of so-and-so age or of this demographic or of this ethnicity and so on. Whereas the operational threshold that we are talking about is basically determines the performance of the face recognition system. Where do you want to evaluate the performance? Like, what is your the point at which you want to measure your face recognition system? So at what false match rate, at a given false match rate, what is the false non-match rate? So how do you obtain those 2 points is based on a threshold. So you pick a threshold, then you get your imposter and genuine scores for that particular threshold from which you calculate your false match rate and false non-match rate. And that's the threshold that we are talking about. So that's an operational threshold to me.
Yeah, I can jump in a little bit. So I won't address face stuff so much just because my company doesn't want me to anymore for the last few years. But one thing that I think is an important point is that when we're talking about confidences, right? I mean, this is very much a question of quantifying uncertainty, right? And neural networks are notoriously bad at that. I mean, they'll be overconfident all over the place, right? So one thing that we're working on quite a bit is really doing better uncertainty quantification from neural networks, both intrinsically or after the fact. And I think this is very important because the more you can, know the limitations of the model, the more it can communicate it to you. It's the model itself is being more humble. It's giving you some sort of humility, and that's the thing that I think is missing, right? When the human is interacting with that machine learning system or the deep learning system, the human needs to know, is like what is really going on, and that's the best way that even if the human had perfect training, the machine also has to help the human in that sense.
Okay, thank you. So from the audience or from in person or online, are there any questions, or should I continue? So there are no questions online to this point. And so let's continue on this theme. And I think Dr. Turner-Lee, your hand was raised for the prior, or is that something new?
Well, I do have a question before you pass on. So
Okay.
with regards to my colleagues here on the panel, so I like this idea of the humility of models. It's like the first time I've heard about this, and I'm familiar with the work of IBM. The question then is, from a policy perspective, just kind of bringing the group back to non-technical people, is that something that should be sort of expressed to folks? Because I think for those of us that are in DC, it just, for the purpose of this conversation, we're often told by private sector, not about, Nisha, the operational threshold. We're often told about the confidence threshold because of the potential or perceived attacks by independent researchers to come in and sort of question the model's thresholds. Curious then, how do we bring that conversation though to non-technical people who are trying to understand the barrage of mistakes or misidentifications that happen when we're talking about the differences between classification or operational thresholds? So just curious, like, how do you translate that humility? I love that concept to people who are trying to figure out, who basically make the assumption that, no, this model is not humble. It actually had intent, right, to discriminate. Where's the humility, right? So just curious, like, how do you translate that for non-technical people?
Yeah, I think, the communication problem is just as hard and just as important as the quantification problem of it. I know, people struggle all the time, right? Not just in this sort of domain, when you're talking about where a hurricane is going to hit, or if the water is going to go over the levee and flood the city, or any sort of thing that you're talking about where there's uncertainty. People have come up with all sorts of visualizations. Do they really work with the general public? I'm not really so sure about it. So I think, turning to our HCI colleagues, our visualization colleagues, I think this needs to be, a very high priority topic. Again, not just in this situation, but in life in general, right? The whole polarization of society is just because we're not dealing with uncertainty in the right way. So the more we can do, I think that would be really good.
Okay. Dr. Sharanovitz, did you want to take a?
I think from a face recognition point of view, I think it's very important for people to understand how exactly it works. Like, I think we as researchers, we understand all the problems, everything. But once someone is kind of deploying it, I don't think they completely understand the limitations of it or how exactly to use it. So I feel like that has to be communicated to people correctly, like how to pick face recognition algorithm, because sometimes they just don't even know the right face recognition algorithm to pick, right? So just because it's top at NIST doesn't mean it's going to work well in an operational scenario. or in a different scenario. So being able to select your face recognition algorithm based on your criteria is important. So that's something I feel like people fail to understand. You can be the worst, you can be the algorithm that's ranked last at NIST, but that algorithm is the one that would probably work under your scenario. So being able to pick your algorithm based on your criteria is very important. I think that's an understanding that people need to, that's something people need to understand.
And one thing I would add on to that is, setting the criteria also for your different use cases in different situations, because, understanding what the values that you're trying to bring forward through the system that you're deploying is also a big gap, I think. So, throughout the day, I think we've heard a lot about, fairness sort of stuff. So what fairness metric do you care about? How much do you care about it in comparison to other sort of metrics and stuff? And all of these sort of value questions, for experts, they're really tough. For people who have no training in understanding what these thresholds are and these metrics are, it's impossible, I think. So it's not just about communicating the results, but also communicating in terms of asking what is the right sort of setting for your system as well.
So I will ask along those lines, Dr. Boyer, to kind of close this this particular aspect of the discussion before going to Dr. Ross. But when we talk about the D prime or the separation of the imposter and the genuine distribution for the some of the algorithms that were actually tested being the best for the African American, which says that the greatest power to differentiate those two groups or differentiates an imposter from a genuine or a mated pair from a non-mated pair was for the African American male demographic. It's just that all of those scores for the African American male demographic were skewed towards higher scores, which introduced the problem on the false match side. So from the verification perspective, in an airport scenario, it all works good from an African American perspective. But when you look at the false match side from a law enforcement or public safety use case scenario, that could be somewhat problematic. But the power, and I think the most important thing that I derive out of the D prime and the power is to say that, it's not one of those things where it is intentional, the way things have been worded in the media in years past, that these technologies not work so well for one demographic group or another. I've never met a machine learning expert that said, I really enjoy making errors on this particular demographic group, right? That's never occurred in my experience. And so I'll ask Dr. Boyer to follow up there, either agree or disagree, and then we have a question from Dr. Ross.
Well, it's a shame that the group that has the highest potential to be best served isn't, right? That's wrong in some academic sense. To come back to Dr. Turner-Lee's question about policy, and to try to be a little more charitable towards the policemen in Detroit than I was, perhaps. If they read the NIST report and they got to the table that said, if I've got a probe and I search a huge data set, the rank 1 match is 99.something% likely to be the right match. And if they sort of internalize that, and they didn't go all the way through the report and get to the part where, well, when you've got this probe and there isn't an image of that person in the driver's license of that state, you're 100% guaranteed a false match, right? If they didn't weigh those and go, okay, I'm in Detroit, what is the probability of the random person that I meet having a driver's license in the state of Michigan? Because I got to multiply that times my confidence I got from the report as my initial gut feeling, right? And the evidence is, at least in a handful of cases that are in the media, that the people on the day-to-day stuff on the ground and the person who's immediately signing the arrest warrant aren't assimilating this information and operating on it correctly. and I hate regulation in this sense, but it's almost like the person needs a special training and certification to be allowed to deal with the evidence from, because, you know, there's these different statistics, and if you don't weigh them correctly, you're going to make a gross error. And that seems to be happening. And I could almost buy into the idea of people needing to be certified to get the face recognition results and act on them or something like that.
Right. Can I jump in before we go to Dr. Ross, just on Dr. Crowley's point? That's part of, Dr. Crowley, that's part of the project we're trying to do at Brookings, right? Trying to give people the right certifications to use these tools. Because I think, and I'm glad I'm not there because someone may yell at me. I think what happens for the layperson is that we're sold on the operational confidence of the model and not necessarily the variance of what Dr. Crowley said, people not reading the actual weighted metrics to determine its predictability. And so when you give an officer a shiny object, the only thing they're going to use is use it because they're actually trained to catch criminals. And that's what they do, right? And they come with their implicit and explicit biases. So I think going back to Kush's conversation, that's where you have to have these distinctions for lay people between what is a company trying to get you to procure in terms of the operational value versus the extent to which that context in which it's deployed that goes back to that humility of the model, actually messes people up because they're convinced that the confidence is really what's driving the efficacy. So I think that's where we get caught up on my side of the universe, where we're like, the model's working perfectly fine because that's what it was designed to do. But the people who are using it to make it work even better, and they're already profiling. So that's part of the problem that we're seeing on our side of the world when it comes to policy.
Well, let me also say that next year, as we host this conference here, I think you would find that the group would be very welcoming to you, and the discussion, and value the discussion from a social context. And now, Dr. Ross, you've been very patient over there.
No, thank you very much. It's more of a comment, perhaps leading to a question, but the comment is related to the observation that in high stakes application, such as the one that we're just discussing about making arrests, I think there should be a fusion of different algorithms, not just a single algorithm. And secondly, there should be a fusion between the algorithm and the human expert. In other words, there should be a partnership, a collaboration enterprise between multiple face matchers, and then also with human experts, all of which are certified. Going back to an earlier comment about scenario-based, I believe it was Dr. Turner-Lee's presentation, there are different applications, and Dr. Srinivas pointed out that an algorithm that works very well in one scenario might catastrophically fail in a different scenario. Without our knowledge, we may not know in advance what the distributions are. And so by using a consortium of algorithms and then using that in conjunction with a consortium of certified experts in high stakes application, we might be able to reduce the error further by simple classical information fusion theory, which talks about decreasing uncertainty, decreasing entropy by using a judicious combination of classifiers. So just a comment, Dr. King, thank you.
Yes. Dr. Srinivas?
Dr. Ross, but if you want to use multiple of these algorithms, right? Like, let's say an organization, if they want to, like the government, like let's say if the CBP, if they have to buy all these, license all these algorithms, it's going to cost them a lot, right? So, and each algorithm also has different hardware requirements, different software requirements. So how do we unify that? So they have to build the infrastructure for it, which is again going to cost them money. So it's kind of like a trade-off. Then it kind of becomes a trade-off between, okay, do we have all this money that we want to spend, or it's kind of like this accuracy.
Right.
So I feel like that kind of comes into question at that point of time.
I think it does, and the important aspect is the nature of the application. I think for certain kinds of applications, we might not need that consortium. But in high stakes application, when there is much at stake, I think that investment would be necessary, especially as AI becomes mainstream. And I clearly appreciate the economical considerations. We don't want to discount that because very often that is the factor that is driving the business model. But at the same time, in applications which is costing lives, I feel that the economical aspect has to be baked in, but also taking into account what the ramifications are of making a mistake. But a good point about the economy of the process.
All right, Dr. Varshney.
Yeah, just one kind of comment. I mean, I fully agree with what Dr. Ross said. I mean, no one would argue that ensembling things is good for accuracy, for uncertainty quantification. I mean, all of it, right? But and kind of related to what Dr. Srinivas was saying, I mean, maybe the answer isn't to take actual like lots of models, but to try to do this inherently in the training itself of a given model. And one thing we've been working on a little bit is something called invariant risk minimization. And the idea is that if you have training data from lots of different environments, then I mean, the bad stuff is always when there's spurious correlations, right? That's what you can really, I mean, point to. So when you train in a smart way using data from several different environments, then what's constant across the environments is kind of like the stable aspect, the causal sort of relationship with whatever the phenomenon is that you're trying to look at. So you can kind of focus the training on those stable causal sort of parts of the features and kind of get rid of all of the spurious sort of stuff. And I think, I mean, in the ideal world, that's, I think, what we should be aiming for if we could do it.
Okay. So let me turn back to the audience again to ask if any of the conversation has spurred a question. Okay, sure.
Hi, everyone. This is a bit of a detour, but I'm really curious as to kind of the question of the fact that we view both race and gender right now in biometrics as so binary. I mean, I think we're kind of moving in a world direction where both race and gender are really way more in the middle. Like, I don't know if you guys have seen those National Geographic projections that like in 20 years, everyone will be mixed race. Obviously with gender, it's become much more of a spectrum, I think, recently. And so I guess my question is anyone doing research on either, say, non-binary individuals or mixed race individuals? And kind of calling back to Dr. Boyer's question earlier about, you know, is there anything inherent about female faces or African-American faces that, you know, causes these issues with facial recognition accuracy? You know, do you think that there's valuable information that we can find from looking at people who kind of fall in the middle of these things?
So who would like to take that first? Well, that's Dr. Boyer, would you like to step to the mic and take that, or would you like?
That sounds loaded enough. I'd like not to be the first person.
You like, okay.
Yeah, I can be the sacrificial lamb, I guess. So one thing I would argue is why do we even do, I mean, these face attribute classification problems to begin with, right? I mean, when is it, like, when do you even need to classify the gender of a person based on their face? When do you ever need to really classify into a discrete category the race or ethnicity? Yes, you can make up sort of use cases. Yes, there are sort of places where it is used, but if you think deeply, I mean, couldn't you argue that there is actually no real reason to do it? So that's kind of where I would start.
Now he's gonna, all right, now.
So one of the scenarios where you would do this came from was it embassy surveillance or something? If you're running an embassy, you got video outside, you see a person around at unusual times and you see them multiple times and you want a description of them, it'd be great to say age, race, height, weight. We're looking for someone like this who's around here an awful lot, right? So there are surveillance type scenarios, intelligence scenarios, where I think getting a description of the person from the video, even though you can't recognize them, you have nothing to match them against, or you've matched them against whatever you've got and you don't have any results, may have some value.
Okay. Dr. Srinivas, would you?
I mean, yeah, we primarily use it for searching, right? Like indexing larger data sets. So you want to keep reducing the search space of larger data sets. So that's where we kind of filter out our, we use attributes at that point of time. So it is important for us in face recognition to do that. But based on the question that the person in the audience was asking, I personally feel like we should completely understand how we're learning these gender features or these age features on the group that we have right now. And then the next problem is, okay, if you kind of completely understand what features are contributing to these distinctions, then we can kind of think about, okay, if it's like a mixed race person or something else, okay, these are the different features that will contribute to it. I feel like we not fully understanding what the features are representing. Like that's kind of like my primary problem. I really don't know how we would be able to tackle the other problem the person mentioned in the audience.
Yeah.
Right.
So I believe that the technology and the application and the use cases have evolved as you've gotten more people involved. As the technology has matured, you've gotten more people involved. From the early 2000, probably the late 1990s, early 2000 timeframe, a lot of the face recognition algorithms were relatively slow. And if you had very large repositories, one of the things you wanted to eliminate first off were very obvious errors. And so when you had men being matched to women and produced relatively high scores, or you had, folks with darker skin tone being matched to someone of a lighter skin tone, in an erroneous fashion, were there some things that you could do to basically, as Dr. Saranovas pointed out, basically reduce the search space? Now that we've entered into an era of, very large scale GPU based processing with DCNNs, I don't necessarily know that from a face recognition perspective, that remains such an imperative. All right, from a face recognition perspective. But, we could actually think in the context of other commercial use cases where they would say, no, this is an imperative for what we'd like to use this for from a commercial perspective. And I got somebody who wants to make a comment behind me, but I also see someone in the audience that may want to make a comment as well or ask a question.
We can't hear it.
So either you're going to have to come up or shorten your question so that I can basically recast it. So you can come up and.
And Dr. King, I have a response to that question too about the binary nature of it as well.
What I just wanted to say, right, I feel like the search space is still a concern, right? Because a lot of things are moving on the edge, right? A lot of the devices, cell phones have now these co-processors that can run neural networks, right? But if you're on a device on the edge, the search space is still a concern. And so, yes, we have large resource available, but if you want to do a lot of these things on a smaller device, you would still like to be able to eliminate some of these categories. So those, okay.
Yeah, absolutely.
Thank you.
Sorry. Yes.
Are you with the?
No, I'm from Los Angeles National. I'm sorry.
Dr. Tornelli.
Yeah, I mean, I want to actually respond to the question around this whole amorphous classification and whether or not we should just get rid of these features overall, just because they turn out to be more problematic. So I do agree with what I've heard so far with regards to getting the feature channel, getting the feature functions right before we actually move into that less binary construction of identity. But I do want to, as a sociologist, sort of forewarn scientists that the challenge that we have with algorithms is the inferential aspect of the model development. So you may not know the exact feature, but you can take inferential behaviors and other attributes and sort of combine that to come up with a taxonomy or a typology of what that person or who that person is. And the challenge that we see this embedded in that does hit facial recognition technology, even though we try to argue that it's a separate technology, is image recognition. When Google's search engine misidentified Blacks as apes, it has a lot to do with some of the blurred lines that we see based on these features or classifications or whatever the scientists call them, but it's problematic. And one of the things to the question that I struggle with in my work is that right now, in terms of civil rights laws and federal protections, they only protect the binary federally protected people. They don't protect people that fall within that gray space where it's not just, it's like LaTanya Sweeney's work. It's not just that you're Black, but the sounding of your name that suggests that you're Black or Hispanic actually serves you predatory financial products. So how you look at that in the context of what's really not, we rely upon, this is what I said earlier, facial recognition for a long time, I always believed it was sort of its own technology, but many of the types of functions are embedded in other, they're either refined in image recognition software or they're used for commercial purposes, but they sort of fall along the same value judgments, as Dr. Varshney said. I think we have to be careful about that because I think that's where people actually get in more trouble. I tell companies all the time, if you're trying to optimize my binary features, then maybe ask me, oversample me, figure out ways to include me. But that's not really where all the noise happens. It happens because I just had a conversation with someone like this who is basically suggesting, well, should we throw in other variables that we assume may be the inferential variables that show up to be able to correct the algorithm for discrimination? Well, you have to make value judgments on that in terms of what's associated with a Black woman who has a child, who shops, whose last name may be X, whose zip code may be X. So I think that's, again, going back to that question, I like that question, but that's where we actually struggle because that's where most of this, the lack of humility in the model happens, right? When we're actually able to pick up these inferential features and attributes and make clear determinations if this is who that person is. And that's where you start to see a lot of the surveillance and predatory stuff that happens along the lines of many of these technologies.
Okay. So Dr. Varshney, did you also have a?
No, I mean, I think I made the point I wanted to make, but maybe one further thing, right? I mean, if we really do think that like having these intermediate models is helpful. I mean, in a lot of other fields, whether it's speech or other things, I mean, they're really moving towards end-to-end training, where really the end task is kind of what you train for. You don't have these intermediate sort of models. So yeah, I mean, and then on the point of doing it on the edge, again, I mean, if you have kind of, I mean, the end-to-end model already, then you might not need to do these intermediate steps. I'm not the expert on this topic, obviously, but I mean, we might be headed there. That it seems reasonable. So. Yeah.
Okay. Are there any other questions from the audience? When we started this panel, it looked like we had so much time to actually hit all these different topics, and here we are about 7 minutes left. And so are there any other questions online, or you got to?
Yeah, one of the things that I would like to push for as we think about next year in this conference and the panels is to drive this into some of the use cases for the face and face processing more generally, where these new algorithms are focused on health and healthcare. We need to inject this into the next year's discussion, because what we're going to see, Dr. Varshney, is that these intermediate models are going to remain. These intermediate models are really important for things like looking at heart rate and blood pressure from facial videos and things like that. So unfortunately, I think we're kind of stuck with them on the face side of it, but I'd love to learn more about what's happening on the other domains, like the language domains, the NLP domains.
All right, so we roughly have about 5 minutes left. And so what I'd like to do is give each one of our panelists about 60 seconds to tell us kind of what do you think are the most critical issues that need to be addressed in the near term as it pertains to demographic performance variabilities and biometrics and related technologies. And I will start with Dr. Turner-Lee.
First, I need to learn how to take my hand down. Hold on. Let me start that. I need an algorithm to do that. So I would just say in 60 seconds, this has been great. I've learned a lot in this panel discussion, just of some things I've been trying to interrogate with my own research. So I want to say thank you for having me participate as a non-scientist. I do think it's important, and Dr. Varshney, I'm going to just keep this in my mind, this humility of the model. For more humility of the model to come on the point of data scientists and computer scientists so that we can actually bring balance to the sociological implications that are currently at issue with facial recognition technologies. And I think doing a better job of that, communicating that narrative is really important. But I would also say this, and I'll just wrap up my comments with this, that I do also think it's important that we have more collaboration and regulatory safe harbors or experiments where we actually test some of these products on real people. There's a conversation that people should have around indemnification and liability and harm, but it's very important that if these products are going to be used on people that are demographically different in terms of faces, that we have to find ways to include those faces into databases, not in a passive way, but in a way that makes sense so that they can be optimized operationally and the confidence levels are better. Because I do think we disservice populations in these continuous normative conversations around bias, and we exclude them from actually helping to solve some of the problems that we're addressing within this community.
Okay. Thank you, Dr. Lee. Dr. Varshney?
Yeah, I mean, I would have said, yes, more about the uncertainties, but yeah, Dr. Turner-Lee covered that. So maybe, I mean, one thing that I would say is, coming back to what I was saying earlier, I mean, more on the interaction aspect. So we know that there's humans, we know that there's people, the policemen, whoever who are going to be using these systems, right? So we need to make things kind of more human-centered. It's easy to kind of stay in your own world and say, I got the 99.99% whatever, but really kind of taking the HCI perspective, working with the actual end users, I think, and understanding where the gaps are would probably be one thing that I would emphasize.
Okay. Dr. Srinivas?
For me, it's all about understanding the features. I really want us to understand what the feature vector is telling us when it comes to like how is it like distinguishing between two people, like what is it learning? So basically more visualizations or activation maps. Like right now we do it with activation maps, and that's kind of what we're going with, areas where it's concentrating, but basically trying to correlate what the feature vectors are learning from the network is something I really want to I hope someone publishes about it or I publish about it and things like that. And the other thing is data sets, right? So building balanced data sets for these algorithms. So I feel like those are the two things.
Dr. Warrior?
Yeah, so I think understanding when accuracy differences occur, understanding why they occur. What is the cause, in the sense that if I change the cause, I wouldn't see it, right? Or cause is of the same one. And which is kind of like what Nisha was saying. And to some degree, what Nicole was suggesting, understanding the use of face recognition technology embedded in a particular application or scenario, and how to better guarantee from the technology side that it's used correctly or appropriately or with safeguards.
So if I had to offer two things, I would say probably from the data set perspective and the protection and privacy, we need better data and we need to balance it with privacy as we have these discussions within the US as it pertains to privacy. One of the things I try to remind the privacy advocates is face recognition is a global technology. So if you stymie its growth in the United States, you won't kill the technology, right? You'll only stymie the growth within the US. The second thing immediately that I think we could do is I've never been an advocate for banning the use of the technology at large. And I've always spoken against banning the technology just widespread. But in that vein, I think commercial vendors, and maybe Nisha, Dr. Sharanavas, you can actually spearhead one of these efforts, is when the technology is being used by local law enforcement, the smaller the department, who are less likely to have the resources and expertise to be able to appropriately be able to deal with potential false matches and basically execute very thorough investigations. Maybe we should actually implement a threshold at some particular level such that, you know, they just don't get the highest score. Whatever match produced the highest score, you know, you don't get access to that. But maybe that particular capability is one that's more or less used at the federal level, where you can deal with, you know, you don't necessarily need a threshold because you know that the resources are there and the analysts are there to actually do a very thorough investigation once the match has been produced. And so the thresholding aspect from an identification perspective, I think, is very important. And I think we have to treat this technology different. I think the technology vendors and the technology developers have to develop ways to kind of protect innocent people from the misuse of the technology going forward. I think it's one of those things that can be done. I think it's relatively simple to do. And I think that it would be an imperative to actually make that happen. And with that, I would like to thank now all of the organizers, and just being respectful of time here. I'd like to thank all of the organizers that have helped with putting together this great workshop, and thank the panelists, Dr. Varshney, Dr. Nicole Turner-Lee, Dr. Boyer, and Dr. Sharanavas, and also the fellow organizers, Dr. Arun Ross. And so thank you all for a very enlightening discussion. And I'd also like to, before we close out, ask my co-organizers if there are any other housekeeping items that you guys would like to comment on at this point.
I think the video will be ready in 24 hours.
Yeah. All right. So the video will be ready in 24 hours. Dr. Ross, you have anything?
No, Dr. King, I think that was a great panel. And I also want to thank the panelists and all the attendees and all the authors. Excellent presentations, excellent discussion. Same time next year.
All right. Yes. All right. Thank you.